Uh, so hello everyone, welcome to this RAS specialist discussion meeting. First of all, we would like to thank the Royal Astronomical Society for giving us this opportunity to host this event. The theme is Galactic Magnetic Fields Connecting Theory, Simulation and Observation. And we wrote a proposal about it, and RAS was very kind to accept it, and then we organized it. We would also like to thank the frontline workers and essential working staff, because the past 2 years, almost 1.5 years, a bit more, has been a bit crazy, as you all know. And we would like to thank and appreciate the efforts of frontline workers and essential staff throughout the globe. With that, I would like to begin this meeting. I'll give a very short introduction, trying to tell what were our views, and then we'll very quickly move to talks. So first of all, when we were thinking this about this meeting, we were thinking what are the questions we should address, and what are the important things to take care of. But to talk a bit about galactic magnetic fields, especially I would like to highlight some of the points which has come up recently in last 10 to 15 years. And some of the points, of course, many of these points would have been in older works also. But to go a bit more specific, like in terms of observations, there has been recently been a lot of focus on observing magnetic fields in high redshift galaxies or young galaxies. This is a very last 10-15 years kind of thing. And then thanks to like LOFAR and Planck, that there has been really been fine scale observations, like observations at smaller scales, which makes it easy to compare with the small scale structure of magnetic fields. And people have been starting about filamentary magnetic fields, etc., etc. And there has also been very recently the FIR, far infrared polarization observations. So overall, this is in last, and some of the points from last decade or so. And in future, it has excellent prospects with the POSSUM survey, which is the Australian SKS survey with Australian SK Pathfinder, or eventually the SK. It has excellent prospect in future. Going into simulations, recently there has been a large number of simulations at very high resolution, including all sorts of physics. And there has been very many simulation at various scales, so a patch of the interstellar medium, galaxy scale simulation, and then cosmological simulations. Especially the cosmological simulations in recent times have recently picked up, where the magnetic field is not just a passive agent, but is also evolved with time. And it has also been recently been accepted that the cosmic rays and magnetic fields can be a good feedback agent from point of view of galaxy formation and evolution. And in future, it would be good to see some of this comparison in much more detail, and how one simulation at one scale can help simulation at larger or lower scales. In terms of experiments, magnetic field experiments, most of the slightly older experiments were for the large scale dynamo or large scale flows or large scale magnetic fields. But with recent laser plasma turbulence, even the small scale dynamo has been looked from point of view of experiments, and it's a very exciting field of this laboratory astrophysics. Last but not the least, from a theory point of view, the linear theory is somewhat understood. And recently there has been a lot of efforts to look at nonlinearities, which makes the connection with astrophysical systems quite direct. So this is just overall a summary of what we had in mind. Of course, I would like to state again, these are not all points. This is some of the recent highlights, and some of these ideas might be there in older works also. So we wanted to make sure that we mix or people from all of these fields and even broader fields, and bring them to at one place. And then we and Luke came up, myself and Luke, we came up with these questions, which our speakers kindly accepted, which we'll be listening today. So in terms of some numbers, there are 9 speakers today. There are 26 pre-recorded talks. I would request everyone to go to website and look at the program. At the end of the program, there are links to pre-recorded talks. And total, we have 97 registrants, 50 who are RAS fellows, and 47 who are non-fellows. Some bookkeeping things that first half of the session before lunch will be moderated by Luke. At the end of the talks, sorry, if you have questions, please raise your hand and we'll unmute you. The questions which cannot be considered today, cannot be considered in the live talks, can go to Slack, and then speakers, please take a look at Slack also for possible questions. And with that, I would like to end the introduction. I welcome all of you again. I'd like to end a quote which I have taken from one of the pre-recorded talks, but it's very interesting. The quote is, "The detection of polarized emission with spiral pattern near the black hole of M87 was an amazing result. Pity that dynamo action was not considered as a possible origin." So we'd like to discuss all possible such pities and also triumphs. So please, with that, again, welcome you all. Luke, please take over. Thank you.
Okay, thank you, Amit. So just to be clear about that, so if you raise your hand, we will promote you and you'll be able to see the mute button and so on. That's just the way it's done at most of the RAS meetings. And the other thing is there's closed captioning is available if you want to turn that on. Okay, so our first speaker is Kandaswamy Subramanian.
Thank you very much, Luke and Amit, for getting me to talk on this small and large scale dynamos. I kind of chose this thing that whether we should say small and large scale dynamos, are they friends or enemies? I asked Anwar, friends rhymes better with foes? And he said, no, foes are too strong. Enemies are okay. So I kept this enemy in the title. Of course, all that I'm going to say has been strongly influenced by a whole bunch of people, and they are all listed here: Pallavi, Luke, Sharanya, Kishore, who is a PhD student, Abhijit Bendre, who is not here at present, Axel, and Anwar, of course. So let me just get into it right away that in summary, of course, we all know that the universe is magnetized, right from planets, stars, nearby galaxies, high redshift galaxies, galaxy clusters, and maybe even the intergalactic medium in the void regions. And the whole challenge is, of course, to explain not only the presence of the magnetic field, which is slightly more straightforward, but the fact that it's so coherent, as you will hear probably in Rainer's and other talks. And the basic idea is that of a dynamo. I'm not going to wear my primordial magnetic field hat right now, but even if it is there, I think we require the dynamo to maintain the field. And all the dynamos that you have are in astrophysical systems are turbulent dynamos. And turbulence basically easily grows small scale or fluctuation magnetic fields. And what I mean by small scale is anything which is smaller than the driving scale of the turbulence. But to grow large scale or magnetic fields on scales bigger than the driving scale, you need some kind of parity breaking in the turbulence, whatever way in which you can think of that. There are different control parameters for the small scale, or I will use this interchangeably, small scale and fluctuation dynamo, or large scale and mean field dynamo, although they're strictly not exactly the same. There are different control parameters. For the small scale dynamo, the basic control parameters will be magnetic fluid Reynolds numbers. And whereas for the large scale dynamo, it's not just that, it's also what I call the dynamo numbers, or in terms of turbulent transport coefficients, things which we call the alpha effect, the turbulent diffusion, shear if you have in the system. So there are different control parameters, so they can grow independent of each other. The saturation, as Amit already mentioned, is the big problem. We don't know, we don't understand it. We have some closure models, which are of course limited by closure. And we have simulations, direct simulations. We have simulations of various kinds, but they're limited by the amount of resolution that you can have in any simulation, which of course means that the whole field is open. The thing which I want to emphasize is basically today I'll be talking more emphasis on the large scale dynamo because there are lots more non-trivial things which needs to be understood there. And a lot more of the audience are now familiar with small scale dynamos. A lot of this stuff is described in a book which with Anwar, which will come out in December 2021, they have been promised. So this is something which is absolutely familiar to everybody, that basically dynamo action depends upon electromagnetic induction. So you have Faraday's law of induction, and your electric field can be generated by both the V cross B term, the induction term, and the resistive term. And you take curl of that electric field. If you have a curl, you have what is called the induction equation, which tells you, given a velocity field, how the magnetic field changes or grows with time. Of course, this velocity is not given to you always. That's the kinematic problem. The velocity also changes, and it gets influenced not only by forces other than magnetic. For example, in galaxy, the gravity is most important, but also by the Lorentz force. So there's some saturation. We all know that in a very highly conducting system, flux is almost frozen. The amount by which flux is frozen is measured by the ratio of this inductive and resistive term called the magnetic Reynolds number. And the amount by which turbulence leads to cascade of kinetic energy is measured by the kinetic Reynolds number, or just the Reynolds number, fluid Reynolds number. They're typically very large for the interstellar medium. If it's fully ionized and you take motions of 100 parsec scales, velocities of 10 kilometers per second, they're like 10 to the 19, 10 to the 7. But you must also remember that galaxies are not just fully ionized plasma. They're also partially ionized for example, in the warm interstellar medium. And then the neutrals can have a significant effect. For example, they can increase the viscosity to make the effective Reynolds number much smaller. And they can also lead to a drift between the charged and neutral components to make some kind of effective magnetic Reynolds number by the ambipolar drift to be also much smaller. So these two become more comparable in some context, and you have to keep this in mind when you're talking about these things. Also, the galactic ISM is multi-phase. It's not just one single phase as most of our models and simulations do, except for a few realistic simulations. The turbulence is not subsonic, it's transonic to supersonic, but many of these complications I will not worry too much about. Just to give you a rapid overview of the small scale dynamo, basically turbulence leads to random stretching combined with flux freezing, because flux is conserved and mass is conserved, B by rho goes as L. And when you have random stretching, fluid parcels typically move away exponentially from each other, away from each other. And this leads to a magnetic field growth. D goes as L, and L keeps growing exponentially. So this is the simple very thing. It always occurs in any random system, provided the magnetic Reynolds number is large enough. And it was actually Kazantsev who first worked out a very nice model for when such growth can occur, and such growth can occur provided the magnetic Reynolds number is larger than some modest value of order 100. Given the fact that all Reynolds numbers in astro systems are much larger, this very modest requirement. Typically, the growth of the field, there's a simulation which I pulled out from Pallavi's work, where you find that initially the power spectrum, this is the magnetic power spectrum against the wave number, it's peaked on small resistive scales where the field concentrates on small scales, but finally it orders itself onto larger scales. That's these black lines. The blue lines are the kinetic power spectrum. Of course, the first of these simulations, which I know of, very good, was done by Niels Hagen, Axel, and Dobler through using the pencil code in 2004, and Shekoshin in 2004. Many others have done simulations after that. Cho and Ryu Pallavi, Sharanya Sur, Amit Seta, and all these results are more or less consistent to show that there's a critical Reynolds number of order few hundred. The field grows rapidly on some dynamical time scale of the turbulence, V by L. The magnetic energy does not go to exact equipartition with the kinetic energy. It's usually even at very high Reynolds number, some tens of percent. And the simulations are, of course, limited. And I said, the way to measure this limitation, which I once learned, I think from Steve Tobias, is to divide the magnetic Reynolds number you achieve by the critical magnetic Reynolds number needed to excite the dynamo. And they're typically of order 20 to 30. Recently, I mean, this is all in subsonic flows. There's been more work on possibility of small-scale dynamo in supersonic flows by Christoph, Federer, Sharanya, Amit, and also very recently there has been some nice work by Fred Gent, which has also showed even in supernova-driven turbulence in the ISM context, you will have this kind of exponential field growth. How it saturates is the big question, as Amit already said. Closure models would predict that you will saturate to so that the field coherence is something like a fraction of the scale of stirring, where there's a critical Reynolds number. But there has been a big controversy in the literature. For example, there is works by Alex Shekoshin where they argue that it saturates more or less on the resistive scale, but this is changing. What we measure in simulations of Pallavi is something like 1/3 to 1/4 for a range of parameters of RM and Prandtl number. The way in which it saturates is very subtle, and I think Amit has written a nice paper on this with Anwar and others, where they look at the PDF of all the growth factors and all the damping factors. And it's not that, growth wins fantastically over damping. It's just that things are growing all over the place, things are damping all over the place. There's a slight imbalance which leads to the growth, and that slight imbalance decreases, which leads to the saturation. More interesting is, if you want to know how to build a model for this, is if you look at not only the probability distribution of the field, but look at the probability distribution of the magnetic energy per unit logarithmic interval. Now, Anwar is one person who has emphasized constantly that the field is intermittent, and you look at the tails. This is the P of B, differential probability. And there are these long wave number tails, which shows there are tails in the field strength. This x-axis is the magnetic field strength, and this is the probability. So there are very strong field regions. It's not a Gaussian by any means. If you multiply that by B squared to get energy, and then multiply it by one more B to just get amount of probability per unit logarithmic interval in the strength of the field. And I got this from Sharanya, who is doing this for some other paper we are writing. Then it's pretty flat in the regime of kinematics. The green curve is the kinematic regime. The black curve is the saturated state. Even in the saturated state, until about 3 times the RMS value of the field strength, this energy contribution is pretty flat, which means that the energy is being in the saturated state also being contributed not only by fields in the general RMS C of the box, in the simulation box, also by structures which are 3 times the RMS value. What it means is that both the C and the structures contribute. So if you want to do any closure, which basically ignores structures to a large extent, it's not completely correct. The structure formation, galaxy formation people face a similar problem, and they build something called the halo model. I can talk about it more later, but something similar maybe needs to be done for this. Let me go straight away to the large scale dynamo. And the large scale dynamo basically is built on helical turbulence. And the helicity of the turbulence, you get, the galactic shear in a disk galaxy winds up 5 components to radial components. And the radial components to 5 components. And the 5 components get lifted and twisted by helical motions, which are driven by rotation and stratification. And to produce back these radial components, you lose something and you get radial field, and you wind it up, you get toroidal field, and there you have an exponentiation going on. It's very nice to draw pictures, and in fact, all nice pictures are drawn by Anwar for our book in this talk. But if you want to do a mathematical representation, you would like to take the induction equation and average it in whatever way you like to average these things. And you get not only the usual induction term due to the mean field and the mean velocity, but you also get something which depends on the fluctuating velocity and the fluctuating field. Sometimes you'll see U here, and that's a remnant of Axel's influence. And sometimes you'll see a V here, which is the remnant of Anwar's influence. So this term, to close this system, you have to express it in terms of the mean field itself. And the standard closure suggests something like something proportional to the mean field, something proportional to the mean current. And this thing goes and adds to the turbulent microscopic diffusion, so it's called the turbulent diffusion. This thing, because people, I think Steenberg, Cross, and Radler gave it the name alpha, it's called the alpha effect. That depends on the helicity of the turbulence, and this depends on the energy density of the turbulence. The thing, if you go to a nonlinear regime, the simplest closures also suggest that this helicity gets corrected by a current helicity from the magnetic helicity. And so, as the field grows, you would imagine that the current helicity grows to cancel this kinetic helicity and saturate the large-scale dynamo. The typical time scales of growth are something like 10 to the 8 to 10 to the 9 years. This has now been seen in even local interstellar medium simulations. And what is the problem? Why am I giving this talk at all? The question is, do small-scale fields which are being generated very rapidly on the eddy turnover time scale, which in galaxies is of the order of 10 to the 7 years at the most, is shorter than the large-scale dynamo growth time scale of 10 to the 8, 10 to the 9 years. So will this magnetic noise completely swamp everything? And all the approximation that we have used in deriving this whole mean field theory, does it break when you take these strongly growing fluctuations into account? And also when this small scale fields saturate because of Lorentz forces, because they're growing faster, they saturate first. And when that saturates, we also saturate the mean field dynamo. These are the questions. A related question is that you are growing the mean magnetic field or the large scale field with these helical motions. Now, magnetic helicity is a well-conserved quantity, thought to be better conserved than magnetic energy. These helical motions, and you have automatically introduced helicity into these mean fields because there are these links between the toroidal and the poloidal fields, which means you have created a large-scale helicity. That has to come at some cost, and that comes at the cost of small-scale helicity of opposite sign. And you can see it in this picture when I take something which represents a flux tube, picture done by Anwar and with his wife Natasha, taking hose pipes in the garden, and you ride it by 90 degrees, you see that this white and black has reversed to black and white. You have introduced an internal twist in the system. Now, if you look at the Lorentz force due to this flux tube, there's a Lorentz force associated with this large-scale ride. There's a Lorentz force associated with the small-scale twist. The force associated with the twist is much bigger because it's got a smaller scales and the currents are stronger. The field strength is the same. And so that guy will come, when you're conserving magnetic helicity, that guy will come and kill your dynamo first, unless you have some way of getting rid of twists, and that's we call helicity fluxes. And if you don't have some way, then kind of an equation for helicity conservation which you can derive, where this flux is zero, this small scale field has gone to some stationary state, shows that the turbulent EMF parallel to the field which is required to grow the field could get catastrophically when there's a resistivity which is pretty small. And so this is a problem. And these problems have usually been thought of as unrelated problems to some extent, but I think actually they are related problems also. But of course, there are problems and there are solutions. And right from 2001, there have been simulations, for example, by Axel, who, in fact, his was the first one in 2001, which showed very clearly the development of a large-scale field, and that you first have, if you first start with a helical turbulence, if you drive helical turbulence in a box, then in the kinematic stage, you get a lot of fields growing on a small scale, the resistive scale, and that grows exponentially fast. And then you come to a stage when you have a very slow growth of field on larger and larger scales governed completely by resistivity and conserving roughly magnetic helicity in the beginning, but dissipating magnetic helicity due to resistance in the end. Of course, since resistivity is very small in astrosystems, this part will never be seen in principle. And even in these periodic boxes, At the most, you can expect up to this kind of time scale, this evolution here. Okay? Where still you don't know whether the field will remain like that or not. So this is the question. My own favorite way of looking at this question, look, how much time do I have?
2 minutes.
Sorry, 2 minutes. 2 minutes to 18 minutes or 2 minutes to 20
Yeah, it's
minutes?
18 minutes.
Oh, okay. Then I won't go into this, my favorite ways. I'll just say that if you actually go to a system where you describe the cousin-safe system with helicity, then you can show very interesting things. What you can show is that the current helicity, which goes to kill the dynamo, it grows as fast as the magnetic energy. And the magnetic energy is given by this ML0T term. And the way it grows is coupled to the alpha effect which you had. So if you have helicity in your turbulence, then the current helicity grows as fast as the magnetic energy. So which is a bit strange because you think there is a both small scale magnetic energy and a large scale magnetic energy. And usually 2-scale models, which people are very happy to do, involves only 2 particular scales, and you're coupling the current helicity, the magnetic helicity evolution, that only as fast as the large scale grows, the small scale helicity also grows. And so the small scale magnetic helicity also grows only as fast. But this model actually shows that that may or may not be true. And what you can understand is that if you take these kind of loops and you have any scale which is slightly, where the field is slightly having a scale bigger than the scale of the stirring, then you're transferring helicity, not just in 2 scales. And so if there's a big scale separation between the system size and the stirring size, then I think much before you grow significant fields on the system size, you will cancel the alpha effect. This is the net message I wanted to convey through that cousin-safe model. But okay, let me not do that. So if you go further in these simulations, then what we wanted to do with Pallavi and Axel was to see whether you can see signatures of both dynamos. For example, if you stir the system helically on a scale, let's say 1/4 the scale of the box, here K is 4, so that you leave space for both large and small scale dynamos to operate, then it turns out that initially the magnetic energy peaks on very small scales, and that can be understood purely from the cousin-safe type of models. But finally, the Lorentz force saturates the field on those small scales and builds up the field on the large scale. But here, again, everything comes because of resistivity. So, and in fact, more recently, I think Pallavi also found parameter regimes, which you can see both these types of dynamos in operation. That is, initially there's a rapid growth, which we think is due to the small scale of fluctuation dynamo, with a growth rate which is about 5-6 times bigger than another stage of nearly exponential growth, not exactly exponential, which we think is due to the large scale dynamo. In this system, there is both uniform shear and it's large enough magnetic Reynolds number and a large magnetic Prandtl number. So we have called this stage where the large scale dynamo is operating, even though the small scale dynamo is almost saturated, but still operating nicely, as a quasi-kinematic large scale dynamo. And understanding this, I think, would be crucial to understanding the large scale dynamo problem. I wanted to flash one piece of work long time done by Luke, which he may or may not remember completely, which is the following. In all these periodic box simulations, the large scale magnetic energy grows and stops growing, and that's it. It doesn't decay. But if you do a mean field model with boundary conditions like vacuum boundary or any realistic boundary conditions, the alpha effect gets killed, but the field does not freeze. The large scale field decays. In fact, this is a time evolution of a one-dimensional in radius and an approximate treatment in Z of an initial seed field. First it grows here in 3 gigayears. At 10 gigayears, everything dies. Unless you have some way of getting out the small scale magnetic helicity. This is with flux, and then you get significant field. So let me summarize in the last 1 minute the story so far. The small-scale dynamo can grow small-scale fields faster than the large-scale dynamo can grow mean fields. And then the question I'm trying to ask is, how do they come to terms with each other? Initially, all scales grow together as one eigenfunction. The Lorentz forces saturate the small-scale field growth before the growing current helicity can significantly cancel alpha. So this is what I'm speculating a little bit. Then we probably have what is called a quasi-kinematic large-scale dynamo, continues to grow the large-scale field. Finally, the small-scale helicity dissipation or getting rid of helicity by fluxes can make the large-scale dynamo efficient. There are two caveats here. One is what I very rapidly mentioned, that periodic box simulations don't show a decay of the large-scale field once the quenching has occurred, whereas solving mean field evolution equation does. So what's happening here? Should we put different boundary conditions? The other caveat is the recent work by Pallavi, where she has shown that if you have anisotropic turbulence, that seems to lead to a distinctly different magnetic helicity evolution, which could in principle alleviate catastrophic quenching. One thing which I should just mention in passing is that the small scale current helicity in some of these cases seems to also decay after some time. So the conclusion is that large and small scale dynamos compete with each other, but they're not enemies. You get enough magnetic energy from the small scale dynamo which can seed the large scale dynamo. The last statement I want to make is that they can actually become closer friends if you have helicity fluxes which depend on the small scale dynamo itself and transfer helicity in space rather than across scales. A lot of the problem arises because you're transferring helicity from small to large scales. But if you have some kind of helicity flux which transfers helicity spatially, that is, you have a divergence of the helicity flux without a volume generation of helicity, then it's possible that some of these problems could be alleviated also. And this is an idea which goes back to Wozniak. Even Luke has even written a paper which I have not submitted because Wozniak has not yet submitted his paper, but we are writing a paper with Kishore on this soon. Thank you very much.
Thank you very much, Kandu. Very nice talk. And maybe we have time for one short question because we're on a bit of a tight schedule, unfortunately.
Axel, please go ahead.
The result about the quenching in the mean field that you referred to, and I think the Luke 2013 paper, I think this is a result that we have so far only seen in mean field simulations, and those are simulations which use the original formulation of the dynamical quenching model. There is an alternative that was proposed by Alex Hubbard and myself, which includes contributions from the mean electromotive force in the fluxes separately for large and small scales. And so this takes care of the quenching, the excessive quenching that we have seen, in particular in galactic mean field dynamo models. So it's, yes, I think, an artifact.
I know that I know that work. Would you then say that there is no problem?
Yeah, I think so, yes.
I would suggest that you should also do simulations without periodic boxes to see whether that is true or not.
Yeah.
Because I mean, I've looked at that paper. I'm not 100% convinced also. So we need to discuss. But at the same time, I agree. I mean, because it's very difficult to know what to put on which part of the flux to put where. And you put something which you could have called the mean flux, I mean, due to mean field, inside the small scale helicity equations. And that also depended on shear, if I remember. If you had a pure alpha square dynamo, I don't remember whether that would still be there. But I think it's important to do simulations where you don't have periodic boxes. and see what happens there. Maybe you may see a different answer, but it's an
Yes.
open question. I agree with you.
Mhm.
Thanks.
Okay, thank you for the question. And we'll have to move on now to from theory to observations with Rainer Beck. So Rainer, if you could share your screen.
Thank you to the organizers for inviting me to give this brief review. And I would like to especially thank Mitya, Anwar, Axel, Kandu, and Luke for many, many discussions about this topic. And they always kept me interested in comparing observations with theory. So I've given talks about this already several times, and I realized that more and more observations we get, the more and more questions come. And I would really like to summarize them here. Just want to remind you, this year is the 50th anniversary of the Effelsberg telescope, and that's why I give some special honor to this telescope. So I would like to structure my talk in 4 parts. I will discuss the 4 different types of magnetic fields we can see: total field, random field, anisotropic, and regular. And so the isotropic random field is characterized by no polarization, no rotation measure. Anisotropic random has polarization, but no rotation measure. And the mean field has both polarization and rotation measure. So the first part is on the random field. So I will not distinguish between random and turbulent, because with our observations, we see that most of the total field is random. And I also don't distinguish between turbulent and random, because in the observations, we have typical resolutions of larger than the turbulence length. So we cannot really resolve the turbulence. We have resolutions which would see random fields on scales of turbulence, but also large. So the first important part coming from observations is that the energy densities of magnetic field and turbulence are very similar. Assuming that equipartition is valid, which Amit and I have shown that is at least correct for large scales. And that is somewhat strange, because simulations say, this is from a paper of Federer et al., that magnetic energy in the small scale dynamo can reach only 10% of the kinetic energy. So maybe further amplification is needed, or maybe the models are not realistic because the Prandtl number and Reynolds number in real ISM are much larger than in the simulations. And another possibility is proposed by Schober, that maybe we are not in the supersonic turbulence regimes, but in the subsonic one, where the level is can be significantly larger. In a paper by Rüdiger Packmore, he got much larger ratios, but still not 100%. The magnetic energy is still significantly below the kinetic energy. So the only paper I know about reaching similar energy densities for large galaxies, 10 to the 12 solar masses, is by Christoph Frommer, a recent paper on AstroPH, and they say they can reach about equipartition between magnetic and kinetic energy. So what the detailed differences between these models are, I'm not expert on. I just want to say that this question of energy densities in the magnetic field is yet not solved. By the way, this recent model by Christoph Frommer et al. Is missing turbulence in the disk, so these pictures are not similar to what we observe in real galaxies. So something is still missing in these models here. The second important information is about the relation between the total magnetic field and the star formation rate, and there's common results from observations by Fateme Tabatabai and Volker Hesen that the exponent is of the order 1/3, and this agrees excellent with predictions for small-scale dynamo. So one by Dominik Schleicher and myself and Rüdiger Packmore, they get also roughly an exponent of 1/3, and that, by the way, explains the correlation between radio and far infrared luminosities. So here, the small-scale dynamo does an excellent job. Now, coming to the detailed local correlations between magnetic field and gas density, you can see the radio and the CO image of M51 look very close. And that indeed is confirmed by correlation analysis that the magnetic field and the star formation rate or gas density, they have very close correlation. But surprisingly, the exponent is significantly lower, around 0.2, than the one of the global. And we explain this as a propagation of cosmic rays away from star formation regions. And that means that the equipartition fields are slightly too high in regions of low star formation. And that makes the correlation flatter. So that is well understood. So summary, random fields magnetic energy density is comparable, which is not confirmed by theory. So we need maybe more realistic models of theory. Random fields are related to star formation, and that can explain the radio far infrared correlation. Second part is about polarized intensity. So this is a tracer of ordered magnetic fields. And just to remind you, the nice plot by Andrew Fletcher, there are two kinds of ordered fields: a regular field, which gives high Faraday rotation, and the anisotropic random field, which gives no Faraday rotation, but still strong polarized emission. So that is a problem for observations, how to distinguish between these two if you don't have very high resolution observations. I just want to mention there are two pre-recorded talks about far infrared polarization with Sophia Hawk by Enrique and by Alex Borlaug, and I would like to recommend to read these talks. And there's recently been new tools to measure the magnetic field orientations in the far infrared with similar resolution of about 10 arcseconds as we got them in the radio range. So far infrared polarization shows orientations in the code gas, which is nicely supplementing the one on the radio. It is not affected by Faraday rotation, but the shortcoming is that far infrared polarization cannot show field directions and cannot measure field strength, whereas synchrotron radiation, synchrotron polarization can do that, and especially synchrotron with help of Faraday rotation can see field directions and also field reversals, and with help of equipartition can also get yield field strength estimates. So let's look at the ordered fields. So that is well known that the ordered fields are indeed correlated with the gas density too, as is the random field, and that has only recently been studied by Alex Borlaug in a paper which is just on the archive, that in M51, not only the total emission, radio emission, correlates with the star formation rate, but also the polarized one. And that is unexpected, because if this would be regular field produced by the large-scale dynamo, how can it react on short scales to the increase in the star formation rate? So what we see here cannot be regular fields, it must be something else. And my proposal would be this is an indication of anisotropic random fields. That means these are in fact random fields produced by the small scale dynamo, which are enhanced in regions of strong star formation. The third part is about Faraday rotation. And this is a tracer of regular magnetic fields, and that can only be done in the radio synchrotron range. And so there are these classical examples like M31. This is recent from last year, a paper by Ellie and myself, this famous emission ring of M31, ordered magnetic field with a small pitch angle. And this is our recent Faraday rotation map. This is the classical prototype of the large scale dynamo field. So we see a systematic pattern of Faraday rotation going from negative to positive. So a nice sine wave variation, which is an indication of the exosymmetric spiral field known since long time. But here there is some second component, which is the BSS, the second component of the dynamo superimposed on M31. But not all galaxies are as simple as that. There's one relatively simple one, 6946, which had magnetic arms. This has ordered field in the interarm regions and has rotation measures which also show a two-sided asymmetry, so positive here and negative there. That can also be explained by a superposition of dynamo modes, in this case, m equal to 0 and m equal to 2. But this is about the simple cases. We have much more complicated ones. And just to compare these with models, so this is a model by Rüdiger Packmore et al. That gives a significantly strong field, but this model, which is only the small-scale dynamo, does not give a large-scale field, has many reversals, and does not show any magnetic arms. So the MHD models of small-scale dynamo are obviously not sufficient. So Rüdiger has improved the models, and in a more recent paper of 2018, he has a similar, this is a vertical field, the radial field, and the azimuthal field, similar results. There's a lot of reversals within the galaxy, which is not what we see in several galaxies. So that is something which is obviously missing the large-scale dynamo action here. Interesting, I come back to that, the variations of rotation measures seen in the vertical field is of the order of 1 kiloparsec. There's another model, which is the modeling the large-scale dynamo by Eva Tormosi, and there's an online recorded talk about this. It gives a very weak field because there is no small-scale dynamo, and that is quite important to note, that without the small-scale dynamo, the large-scale field has some similarity to observations, but the strength is missing. So we need a cooperation. So small-scale and large-scale dynamo are indeed friends, as Kando has said. We need the small-scale dynamo for amplification, and we need the large-scale dynamo for structuring the magnetic field. But unfortunately, to my knowledge, there's no global MHD model combining the two dynamos at the moment. So we can say the magnetic arms we see in galaxies is a signature of the large-scale dynamo, because there's almost no other way to do that. There are several details, proposals how to explain the magnetic arms. So it's a m equal to 2 modes. That's one proposal by Robert Rode. Non-axisymmetric velocity field, that is by the group in Krakow. There's a proposal by Luke, a coupling between density waves and dynamo waves. David Moss, and we'll show this in a second, has proposed that turbulent field is injected in spiral arms, which disturbs the large-scale dynamo. And then more recently, Luke has proposed that the mean field dynamo is suppressed in spiral arms by fast outflows. I just want to mention this one here by David Moss. This is not an MHD model, it's a dynamo model here. And by increasing turbulence in the spiral arms, you can distort the large-scale field. So in this case, in the spiral arms, the small-scale dynamo is an enemy of the large-scale dynamo because it disturbs the field on much smaller scales. So that is not a full MHD model, that still needs to be done. Now to a very interesting result of M51 by Maya Kirdorf recently. We don't see any large-scale dynamo mode in the rotation measures. We see strong fluctuations of the scale on the scale of 1 kiloparsec. That could be vertical fields, that could be high dynamo modes, and that could also be tangled regular fields. And that is something which needs more analysis here. And 1 kiloparsec scale is what Rüdiger Packmore has found in his simulations. So there are only 3 dynamo modes recorded so far, 0, 1, and 2. This is from a recent review by Luke and myself, but there certainly are more higher dynamo modes. But at the moment, we are not able to measure them because lack of sensitivity, lack of resolution, and also lack of proper software. And to compare these 3 field components, this is also from the review by Luke and myself, and Elson and Eric Blackman. We also compiled the field strength. So the ordered field is relatively strong. It's about half of the total field. The anisotropic field dominates. So the ordered field is dominated by the anisotropic field, and the regular field is quite small. This is in agreement with dynamo models, but this anisotropic field, this is something which worries us a lot. So what is the reason for this strong anisotropic field, not accompanied with Faraday rotation, and which is not a large-scale regular field here? So there are different proposals what the anisotropic field could be. It could be tangling of the regular field. And there's some work has been done by Amit Seta saying that tangling is not very efficient. It has only linear growth. Tangling generates only large scales. Fred Gent has shown that recently. And as Amit has told me, tangling needs a large scale field to work on. So that means anisotropic fields should not exist in small galaxies, which is not the case. Small galaxies also have ordered fields which are mostly anisotropic. So could that be projected vertical fields? Maybe. There are no models on that. And maybe the anisotropic fields are anisotropic turbulent field, because it's well known that subalfanic MHD turbulence is anisotropic, and it could produce thin filaments. In a paper by James Beatty, I think he also gave a talk on the pre-recorded talks. So that could be a solution, but we need to know more about the anisotropic fields by further simulations. So my summary of the ordered fields is that, and also of the regular fields, we have ordered fields in the interarm regions. We have Faraday rotation, which gives large-scale pattern, but we need higher resolution and we need software to identify higher dynamo modes. My request to theory is that we need combined models of small and large-scale dynamo. We need to know the spectrum of dynamo modes, so how many large modes are still existing. We need MHD models of anisotropic turbulence. We need to know their scale and their spectrum, and we need models of field tangling. In which galaxies do they exist, and how important is field tangling of regular fields in galaxies. So very briefly, my last part, galactic halos. And there's no talk about the Changes project of edge-on galaxies from the JVLA, and that is has been very, very successful to study magnetic fields in halos. So first, a very important result for dynamo theory. So parities of large-scale halo fields are all even. And that is nice, because that is expected by large-scale dynamos. So we did not find any odd parity so far. Okay, this statistics is still low, but we are optimistic that will turn out. Fields in edge-on galaxies are not simply quadrupolar or dipolar. They are much more complicated. They are X-shaped. They sometimes show reversals, and they are sometimes helical. So this part here and this part here shows clear evidence of helical fields. So the fields in halos are much more complicated than to very simplistic dynamo models like quadrupolar or dipolar, or even more complicated in this galaxy 4631. Carolina Mora has found, again, an X-shaped, but in the Faraday rotation, she detected a periodic variation, which we interpret as giant magnetic ropes. So the field is quite complicated. And so they are symmetric, they are vertical, have X-shape, but they are complicated. And as far as I know, there are no dynamo models including outflows so far. So that still needs to be done. So good news for the dynamo communities. There's a lot of evidences for the action of large-scale dynamos, in spite of the details I've discussed. So magnetic and turbulent energies are similar. Spiral patterns exist. Large-scale regular fields exist in many galaxies. Exosymmetric spiral fields seems to dominate. There's no preference of one direction of the radial component. I had no time to talk about that. And vertical symmetric fields dominate. So in altogether, we have a good evidence that there is a large-scale dynamo. We need the small-scale dynamo for the field amplification, but going into details, still a lot has to be done. And that needs much better observations, higher resolution. And JVLA is one thing to go, but the dream of the radio astronomers is the SKA, and we'll talk about this later. So we expect a total emission from very high redshift galaxies. We expect polarized emission from medium redshift galaxies, and we should be able to see large-scale patterns of Faraday rotation for relatively nearby galaxies. So SKA is the ultimate radio telescope, and please listen to Sui Mao in a few hours. Thank you.
Thanks very much, Rainer, for a nice talk. And we'll take questions now. Please raise your hand.
First one is by Anwar. Anwar, please go ahead.
Thank you. Rainer, when you were talking about the correlation between star formation rate and the field strength, there are also reasons to expect such a correlation for the large-scale field, if the mean field dynamo indeed is controlled by the outflows which carry magnetic helicity to saturate, and outflows are related to the star formation rate.
Right.
So it's not that it's completely impossible.
It is indeed there's indication. I had no time to show that. There is a paper by Fatime Tabatabai showing that indeed the ordered field is related to the star formation rate. But again, we are not sure whether this ordered field is a regular field or the anisotropic turbulent field, because we know that the turbulent field is related to star formation. So that will be another interpretation. But indeed, this is something we should look at. Yeah, thank you.
The next question is by Vasundhara. Vasundhara, please go ahead.
Hi, Rainer. Thank you so much. I just wanted to ask one small question. I know you mentioned that for equipartition, it's hard to say something on equipartition, but you showed us a model from Frommer. Is there any estimates by any chance on electron distribution, electron energy density, for example, in the non-thermal component? So I'm thinking in terms of equipartition between magnetic fields and electron distribution, if they talk about this, because I've not seen that mentioned anywhere yet.
So from observations, this is very hard, because other than equipartition, we don't have much independent information about the cosmic rays. So there's possibility with gamma rays, but this is very, very only for very, very bright and nearby galaxies. From theory, it seems that equipartition is not. I think most papers say that equipartition between magnetic field and cosmic rays is not valid. So there are more or less strong variations between the two energy densities. This is what I remember from models. Maybe
Okay.
Rüdiger can comment on that, or Amit. I think this is so equipartition. So theorists don't like equipartition. This is why Amit and I wrote this paper to say, where is equipartition valid? Where is it certainly not valid? So this is an open topic. And as long as we have to rely on equipartition in the radio range, we have to live with this uncertainty.
Okay, no, I was just wondering, especially now with E Rosita observations, now that you have some thermal energy estimates, if there has been work being done to push equipartition to see different components. So I thought if somebody is looking at all these three topics together.
Yes, so that will be possible in future. Yes, I hope so. Thank you.
Okay, thank you very much.
Okay, thank you for that question. And I think we have time for one more.
So Brian, please. Next question is by Brian. Brian, please go ahead.
Hi, Brian.
Hi, Rainer. Hi. Interactions. We've seen in limited observations we have that some interactions strengthen magnetic fields, and sometimes they remove magnetic fields in the galaxy. Is there some sort of overall systematic picture of the way in which interactions adjust the different components of the magnetic fields, or is it just dependent details on the type of interaction and the stage of interaction?
Oh, this is a difficult question. So there have been papers by David Moss showing that interactions can enhance the higher dynamo mode, so the non-axisymmetric dynamo mode. So this is one possibility. But indeed, sometimes the interactions can really be very bad for a galaxy and remove the gas and also remove part of the magnetic field. So I think it depends on the stage of the interaction and on the intensity of the interaction. There is a paper by the Krakow group studying different stages of interactions compared with the magnetic field strength. I don't remember the details now. There's one paper. I think it's Blage in Krakow. But this is the only paper, phenomenological paper I know about.
Okay, thanks again, Rainer. And we'll now move on to the next talk by Marijke Haverkorn. So Marijke, if you could please share your screen, you can go ahead. I'll give you a 2-minute warning at 18 minutes.
Okay, thank you, Luke. Good, you should be able to see my screen. I hope. So thank you very much to Amit and Luc for inviting me to give a talk at this meeting. But you also gave me a tough talk, a tough topic, I think, to talk about what are magnetic scales in the ISM and to what extent does the scale separation in galactic magnetic fields exist. And now theoretically, as we heard this morning by Kandu, on the second question, there are definitely ideas, and you can, by numerical simulations, you can actually follow the time scales and all the different scales. This is much harder observationally. And the same thing, magnetic scales are so difficult observationally to disentangle. And the more we learn, the more, everything seems to be connected and correlated, which may be a complication, but maybe also a help. And so I try to, in this talk, I'll focus on the observational part, obviously on the Milky Way only, where we can really probe the smallest scales, and try to give you some idea of some of the recent work that, and some recent conclusions and questions on different scales in the ISM. And let me start with a very basic idea to get the, sorry, to take you along in my thoughts. If I can, yes, here. This is an observer's view of a galactic magnetic field, right? To the right, the regular field with spiral arms with constant magnetic field strength, and to the left, the random part of that, which is here modeled as just a random Gaussian field. We all know that, of course, this is not the case. As for instance, you can see with Amit's recent simulations and many other numerical simulations that show that is everything but Gaussian random, the turbulence in the ISM. And also the regular fields are not as regular as in these models, as shown, for instance, by different observational probes. In the top, you see a beautiful Planck image where the lines give you the magnetic field orientation. And although you do see the large scale field that follows the spiral or it follows the galactic disk, it's obvious that there is a lot of small scale structure in this large scale field, partially induced by things like dust clouds. And the bottom part is from this study by Patrikiev that Rainer also mentioned earlier, where he tried to follow the spiral arm ridges in M51 in different tracers in CO and synchrotron intensity and dust and polarized intensity, and also showed this also showed smaller scale structure in the otherwise regular magnetic field. And so Rainer already talked in detail about the third component that we can include to try to get a bit more handle on the different scales, which is the ordered magnetic field, or also called striated, and which Rainer called the anisotropically random field, which turns out to be a large part of the magnetic field, as Rainer said, in external galaxies, which may be not so surprising, right? Because you can make it fairly easily from compressing random field by shock waves or shearing by, for instance, galactic differential rotation. And so on the right, you see a nice image drawn by Andrew Fletcher to give you a visual on that. So now with that background, how I would like to interpret the questions that I was asked to discuss is just give them an observational tweak and look at these very concrete questions. Can we observe magnetic field coherence scales in the diffuse ISM? I say diffuse ISM because I'm not going to touch on molecular clouds, which is an whole other story. Are fluctuations turbulence, or are they discrete structures? And can we use proxies to probe the scales in the magnetized ISM? If we cannot observe the magnetic field directly, are there things that correlate that we can use to probe these scales? So let me start a while ago. This was back in ancient history when I was still young, and I still thought that things were simple, where we would probe the magnetic field scales with structure functions of rotation measures. You could get different slopes here of the structure functions that here Minter and Spengler interpreted as the transition from 2D or 3D to 2D turbulence on smaller to larger scales. Or here this study that we tried to show that structure functions were different in arms and interarms. And in interarms, they had larger scales, coherence scales of the rotation measure structure than in the spiral arms. And Niels Oppenheimer did this in the on the holes for the whole galaxy, for the whole sky, in his all-sky map of rotation measures from extragalactic sources. He subtracted the galactic latitude dependence of these rotation measures from that and made a structure function here in the solid line of all the structure that he could see in rotation measures in the whole galaxy. And you see the structure goes up to about 100 degrees, which is, I think, also obvious here from this, this image where you see these big positive, negative rotation measure blobs that must be dominating the structure at the very large scales, which of course is not turbulence. It's not, but is well, possibly an indication of an odd dynamo structure in the galactic halo, not in the disk. But here you see also already one of the problems with these rotation measures, right? There are a number of these problems that the rotation measures, especially for these extragalactic sources, are integrations along the whole line of sight. So you never know if this is local, but large in angular scale, or whether this is global. The magnetic field information is weighted with thermal electron density, which is generally a problem in all of these magnetic field measurements, that they're weighted with some other ISM component, and that there's no distance information. And so now we're slowly trying to mitigate some of these problems. And one of the very promising techniques is Faraday tomography, or rotation measure synthesis, which I'll not explain but in detail, but show you a little bit by these two fields here. This is one field, and these three images at the bottom, let's start there. These are three images of exactly the same field in the sky. What you see is polarized intensity at a certain rotation measure, or at a certain Faraday depth that is given here. And so the polarized intensity structures are all very different in these three slices in the sky. You do see extragalactic point sources here with some artifacts over. And of course, the darkening at the edges is due to the attenuation of the telescope sensitivity. So in fact, this intensity is field filling. And the intriguing thing here is that if you go to different Faraday depths, the structure in this field is very different. It seems filamentary, but fairly straight and in all kinds of different directions. This is also very nicely visible in the top field. This is a study by Weber-Jelic et al. There, the colors show the different Faraday depth slices. And this again shows you large-scale structures in different directions. Larger scale structures, but also these very narrow depolarization canals that can be very long and are surprisingly straight. Now, this field has been follow-up studies have been done trying to find the correlations with other ISM components. And here on the left, you see a very nice result by Salim Zaroubi, who overlaid over exactly the same field, right? The colors are exactly the same, but he overlaid dust polarization orientations from Planck. And it is clear that these two are correlated, right? The directions of the Faraday depth structures with the direction of the dust polarization, which is not necessarily a given that it should, right? Because your Faraday depth depends on synchrotron emission, on thermal electrons, whereas the dust polarization is created in dusty magnetized regions. But it means that so the magnetic field has to have some coherence between the dusty regions and the ionized regions that can probe both. I should also say Zaroubi looked at two other fields nearby in the sky which do not show this particular correlation. So it is true in some parts of the sky, but not all. And so to the right, you see a follow-up study by Kalbala and Kerp, who looked at H1 neutral hydrogen in the same field. And at some velocity slices here, this is shown here in the blue contours, they saw filaments that were exactly aligned with this Faraday depth structure, which you see in the background in the white and orange. And so they took a power spectrum of these H1 filaments, and this power spectrum is shown here in black, which gives you an approximately Kolmogorov slope. But then if you look at the power spectrum parallel to the filaments and perpendicular to the filaments, which is here, the red and the green, there's a very clear anisotropy in this turbulence, right? Which you also see here in this. This is all in the same velocity slides. And you can also see it in the maps. So even though this power spectrum shows you nicely Kolmogorov-like turbulence and a consistent slope, it is very clear that here this turbulence is very anisotropic, and it is connected to this large-scale magnetic field orientation in some way. So this is in one velocity slice, or a small range of velocity slices, and there's no anisotropic correlation in different velocities. And so ideally, you would want to connect a distance to this, because once you have distances to these structures, then you have scales, right? Then you have physical scales and not only the angular scales. Now, in this part of the sky, it's quite impossible to translate velocity, H1 velocity to distance. So we'll need another tracer, and this other tracer that can be used is starlight polarization, because thanks to Gaia, we have distances to lots of stars. And the polarization of almost all stars is due to interstellar dust in magnetic fields. And so by combining that, we can get a handle on distance, is the idea. Now, unfortunately, that was not possible for this field, where there are only a few stars available with polarization measurements. But here is a very nice result from a field that is really only a few degrees away. This is a recent paper by Luka Turic et al. And Luka here showed the polarized intensity in this field. And in the middle, in the blue and red, is the Faraday depth, the Faraday depth of the peak of the spectra in every pixel, in every location in the sky, right? Where red is positive and blue is negative. And so you see different kinds of structure in this field, but most notably, there is this almost vertical and almost horizontal structure, which is not quite horizontal and vertical, but almost. This is easy to see in the picture, but Luka also proves this statistically by using the Röhrling-Hopf transform to show that really these two directions dominate in this field. And now the right-hand figure shows you the same Faraday depth structure in the background, in the colorful background, but overlaid on this are stars with polarization measured. And these are the lines or the arrow margins of the polarization directions. And it is immediately clear, maybe also because the stars are color-coded, that some of these stars have horizontal-like polarizations, and the rest of the stars are all more or less vertically polarized. Now, all of these stars have distance measurements. So if you look at the distances, you see something surprising, that here's the polarization angle as a function of distances. And so all the blue stars, remember this is polarization angle, so here the plus 90 is the same as minus 90. So all the blue stars are actually nearby stars and are concentrated around a polarization angle of about 90. Whereas all the pink stars, they are farther away and they all show a concentration around approximately 0, which exactly matches the two dominant structures in the Faraday depths, which are given here by these red stripes. And so what must be going on is that there is some dusty magnetized structure closer than about 120 kiloparsecs that causes the polarization of these blue stars in a certain direction, right, with a magnetic field that is coherent in this horizontal direction in these coordinates. And then suddenly there's around 200 parsecs, there must be another dust screen with a magnetic field that is in exactly the opposite direction, either oriented or directed. So it can be either coherent or an ordered anisotropic random field. And that then dominates, and it dominates all the stars that are in the several hundred of parsecs after that, but still their polarization must be dominated by either a one narrow structure or a very coherent structure over all these hundreds of parsecs. So maybe something like this, something like an ordered field that can be compressed into two different dust slabs or dust structures. And I guess the one logical explanation for the nearest of those is, of course, the local bubble wall, which might be one of these causing this magnetic field structure. Now, Susan Clark tried to do this on a much larger scale, and she looked at the correlations first here in the top, correlations between starlight polarization here in the stripes, the white stripes, and dust polarization from Planck. These two are very well correlated, which is no surprise, right? Because it's the dust that is emitting the polarized emission and the dust that is polarizing the starlight. So these two are very well correlated. This also turns out to hold for here at the bottom for H1 neutral hydrogen. This is from the GALFA survey with Arecibo. And again, Susan has observed very narrow H1 filaments, which she calls fibers, and these again seem to correlate very well with the dust polarization or with the starlight polarization. So this indicates that these filaments, these fibers, are shaped by magnetic fields and that are dust well mixed between the dust and the neutral hydrogen. But the good thing about the bottom map, about this neutral hydrogen, is that we actually have these velocity slices, right? This again is a 3-dimensional data set. And what Susan did in a follow-up study together with Brendan Hensley is she looked at how coherent these hydrogen filaments were in direction for different velocity slices. So how in the third dimension, in some kind of a distance dimension, how these, if there was a large variation in H1 filaments, interpreted as a large dispersion or a variation in magnetic field, this would correspond to a low dust polarization, so a lot of depolarization. Whereas if you had very coherent H1 filaments, it was a high dust polarization degree. And this is what they called magnetically coherent regions in the sky. Again, this is difficult in most parts in the sky. It's difficult to detect distances to this, but this is a first step, I think, to some kind of, again, a measure of magnetic scales in the ISM. Now, one study that does this really nicely in detail is by Gina Ponopoulou, where she looked at here 2 regions in the sky. The colored background is H1, and these 2 circles are 2 fields that she looked at with starlight polarization. And one of these fields, the black one, has 2 H1 clouds at different velocities in its line of sight, and the other one has only 1 cloud in the line of sight. So as said, she took polarization measurements of a lot of stars and looked at their polarization degree and the polarization angle as a function of distance, and could therefore, because of these 2 fields, she could disentangle the polarization caused by the nearby cloud and the far cloud in one of these fields. And so what she found was, again, in these H1 filaments, the magnetic fields as probed by the starlight polarization was in the direction of the filaments. And so now with these stars, you could actually pinpoint the distances to these stars. You could actually start to pinpoint the distances to the H1 structures. And this is exactly what you need, right? Because distance is physical structure.
2 minutes.
Thank you. Then in these 2 minutes, I'd like to discuss the last thing that we're trying in with the Interstellar Polarization Survey, which is a survey of a few dozen small fields in the sky observed in V-band linear polarization. The survey is led by Antonio Maria Magalhães, and the orange dots are a number of these fields. And here is a close-up of one field of 0.3 by 0.3 degrees, and this is data analyzed by José Versteeg. You see, especially in the fields, you have a few hundred stars per field in the galactic plane, and fairly coherently oriented polarization directions. Now, José looked at the general statistics of this field. We have distances, thanks to Gaia and Friedrich Anders, of about a few kiloparsecs, mostly between 1 and 3 kiloparsecs. A degree of polarization, which is very reasonable, a few %, and polarization angles in these fields are centered around 90 degrees, which is the galactic plane, but with a fairly wide dispersion. And so from this polarization degree and angle, there are all kinds of things that you can learn. But for now, I'd like to concentrate on the average orientation of the plane of sky magnetic field and the tangling of the magnetic field. And this is a plot by José Versteeg of the average orientation of the polarization of stars in every field, where the black lines are this average orientation, and the background is, of course, Planck dust polarization. And this still intrigues me, that the 2 of them are, well, you see that if you average everything out, it's about 90 degrees along the plane, but there are very large differences. And both Planck and the starlight polarization often correspond to each other. But then if you look at this field here, now we know there are stars here that are 100 parsec distance, stars that are 3-4 kiloparsecs distance, and they all are very coherent. And so this probably must indicate that there's some coherence in this large scale magnetic field. You don't see changes as you would in a turbulent field or something like that. But you see it being very coherent over, well, maybe kiloparsecs, at least some coherent components. Here, this is the same thing in GPIPS, the infrared polarization survey by Dan Clemens, who then looks at longer distances, but also sees this kind of mesoscale changes in magnetic field orientation along the plane. And the last point I would like to make is that, of course, from the differences in the polarization angles of these stars, in principle, you could find a different magnetic scales. And this is work by Jennifer Angarita, who is looking at this for many fields. This is a plot that she literally gave me yesterday. So it's very new and preliminary. But what you see here is the structure function of this, the dispersion in angles as a function of angular scale for different distance bins in these fields, of stars in these fields. And so for the nearer distance bin, it seems that the structure is increasing up to a certain scale that corresponds to 1 or a few parsecs, and then evens out, and then we don't know yet what this is. And then if you go to longer and longer path lengths, the dispersion goes down and down, which you would expect because any turbulent or small scale structure in the magnetic field is averaged out with longer and longer path lengths. So this is very preliminary and there's no conclusion yet, but I think this gives an idea of how we would be able to try to probe scales in the magnetic field in the ISM with starlight polarization. And I think in the interest of time, I'll just leave my summary up for a minute and I'll ask for questions, please.
Thanks, Marika, for a very interesting talk, and please raise your hands for questions. So I don't see any questions so far. Marika, could you perhaps comment on efforts so far to compare these various observations with theory?
Mm-hmm. I can't comment much, I must say. I have the feeling that at this point, the two are very far apart, right? Because we don't have any physical scales yet. We have indications from some of these new surveys. But I think the first thing we'd have to do observationally is increase the number of starlight polarization measurements drastically, which now the Pacify collaboration is doing in the northern and southern galactic caps, which the South Pole collaboration aims at doing for the whole southern sky soon. And that is the point when you can start to put distances to these scales, have physical scales, and then compare more logically to theory and simulations. But there may be people in the audience who know more about this than I, who can comment.
Thanks. Yes, now we do have some questions in the...
Yeah. Next question is by Anwar. Please go ahead.
Thank you. Marika, it's really very recent and exciting progress, but won't it be useful to look at the structure functions and other tracers, not only in Faraday rotation measure, because it is an integral quantity. You can expect that the correlation length in array can be much larger than the correlation length of magnetic field or electron density. But then, if looking simultaneously, or at, for example, structure functions of synchrotron intensity fluctuations, polarized, unpolarized, and so on, just putting many tracers together, would it be possible to do such things?
Yes, definitely. And actually in the, I've tried to do this earlier to compare the different structure functions and different spectra of total intensity surveys, synchrotron intensity, polarized intensity surveys, rotation measures, and found that it's a big mess, and a lot of it depends on the resolution of the survey, of the specific places in the ISM where you look at, and so especially polarized intensity is very hard to to interpret due to the different depolarization mechanisms. But yeah, definitely there are many studies, I think mostly in the first decade of the 21st century that do that. And now a new way that can be tried is then these structure functions of starlight polarization dispersion. Structure functions, or things like the Davis-Chandrasekhar-Fermi method, or an update by Rafael Skalidis, or similar methods by Hildebrand. So there are a number of recent developments there that try to look at starlight polarization. And the good thing is that, well, again, distances, I've said that too often already.
Okay, I think we should take the last question and then carry on to the next talk.
Yeah, so by Vasundhara, please unmute yourself.
Hi, Marika, thanks so much. So I just have a very quick question, and I think it's related to Mike Peel's comment. Using dust polarization, they have started estimating distances now, and especially for loop 1. There is an estimate that it's more of a local phenomena than galactic, and I'm referring to North Polar Spur here. I'm just curious whether how this can help more also in galactic magnetic field modeling, especially from the polarized emission, because now you can probably put some constraints. So do you know, or like, has there been any work done in this direction, or have you just I'm just asking as out of curiosity about this.
Mm-hmm. Yeah, I think in the studies of the large scale field, the North Polar Spur was always more of a nuisance, right?
Right.
And is traditionally just masked out to look at the rest. But now with these new studies, also it's just published a study by Jennifer West, who says that actually the fan region and the North Polar Spur are structures on the local bubble wall, and are the same thing, or based on the same thing actually. And then I think, yeah, we might slowly. You mean in that instead of masking, you just model it correctly and subtract it.
Yeah, I'm more interested in the halo region, and now you have two contrasting sites. One is from the Rosita collaboration, who put the North Polar Spur region within associated with the Galactic Center event, and then you have the dust polarization community who says that it's more of a local event based on dust polarization. So I was just curious, which direction should we head to if we want to model galactic magnetic field, because you need to have a halo model, and the halo is very weak in the current fields that we have.
Yeah. I personally am skeptical if we ever can model it well enough to fully subtract it. So I don't know if that's ever going to be possible. Maybe we just have to live with this contamination and work around it. I also remember a recent paper, but I forgot who wrote it, that said that the actual North Polar Spur is not one spur, but it's many different structures, and some of them are local and some of them are in Galactic Center, which is a nice compromise, I guess, between the two points of view. But I wouldn't know the answer.
All right, thank you very much. Thank you.
Thank you, and thank you very much, Marika. And now I think we should go straight on to the next talk, and that is by Anwar Shukrov. So Anwar, if you could please share your screen, and you can get started. I'll give you a 2-minute warning at 18 minutes.
Yep, thanks. So can you see my screen? Is it okay?
Yes.
Good. So I was, my title is Dynamo Theory and Simulations, and probably I should have said and simulations and observations, because theory, simulations, and observations are all three equal parts of our attempts to understand what's happening in nature. And I was asked by the organizers a very provocative question to discuss this question: is the mean field dynamo theory useful in the age of direct numerical simulations? Well, I tried my best to address this question, but perhaps not exactly as the organizers wanted me to do. But to me, the answer is definitely yes, for a very simple reason. The complexity and realism of modern numerical simulations is approaches the complexity of real life, of what we see in observations. Then just even reproducing very accurately what we observe doesn't solve the problem, because, okay, fine, we have another observation, as another picture as complex as what we have observed. The only difference is that you can run your computer several times, changing parameters. Otherwise, you see in front of yourself a picture as difficult to understand as we had before simulation started. So in this case, models necessarily simplify. They need to be simplified, and the simpler, the better. Such models is the only way known to us to understand what's happening. Then, the more realistic are the simulations. Perhaps paradoxically, the more important are simple analytical models. It's not that simulations can make simple models unnecessary. No, they make them even more necessary. So simulations, even completed, when you have your final results, the simulation is finished, the code hasn't crashed, you have a fantastic picture. Yet it's not a result as yet. It's a tool to understand physics. Likewise, observations. The better the observations, the more questions we have. The simulation observations are tools to understand, not aims, not final goals. Well, but then how to compare simplified, very often oversimplified, and yet useful models with complex simulations, with complex observations. And here, there are plenty of details which can decide how successful or otherwise such a comparison can be. And for example, a simple question, what is the mean field? Is the uniform field extending from minus infinity to plus infinity across the whole universe? Or probably not. Across the whole galaxy, can it be curved? Does it, what must be its scale? So what is a mean field? I want to discuss this. It's a highly non-trivial question, despite its simplicity. And then I will discuss something which I can see with pleasure from the program of this meeting. Many people are thinking about this. What is the evidence of dynamic action? Now, there is a whole range of MHD models of galaxies, forming galaxies, young galaxies, evolving galaxies, local ISM simulations. And many authors claim that they see dynamic action. Can we be sure? What is the evidence of dynamic action? So this is my plan. So what is the mean field? Well, as Kando explained, if you have a partially ordered random medium, random in most real situations is turbulent, but not necessarily, then any variable can be decomposed into the mean quantity, which I most often denote with capital letters, and angular brackets. Angular brackets mean averaging, and fluctuations. Where possible, I use for fluctuations lowercase characters. When it's impossible, I use a dash. So this will be the notation I will be using. Here, these angular brackets denote an average. And very often I myself, in my papers, I would write in this place in a paper, a suitable average. And this is the problem. What does it mean, suitable? There is a whole range of possible averages. Ensemble average is the one used in theory, where you average over the probability distribution of your realizations of random process. There can be, in simulations, people use special averages. In three-dimensional volume averages, averages over planes, averages, for example, in azimuth in spherical domains, time averaging. There is also filtering approach, where you smooth your random field, for example, with a window, Gaussian smoothing or top hat filter, sliding average, or Fourier filtering. They all potentially give different results. And here, and these differences can be important. By the way, I was pleased to find out the source of this widespread quote. So the mean field equation, which was shown by Kondo, it's a simplified form of it, which I presented, is obtained for any averaging procedure. There's this attractive feature of averaged equations, which Germano in his 1992 paper called the invariance of turbulent equations. For any of the widespread averaging procedures, the form of the equation will be the same. It's good news, but the meaning, the form, the structure of the mean fields and fluctuations will be different, depending on which averaging method you use. And in particular, regarding the mean field theory, there is a very widespread assertion, especially widespread among theoreticians, that the mean field equation from the previous slide, this equation, it only applies when there is a wide scale separation between the mean quantities and fluctuations. In fact, that's not true. This is only true in some of the methods to average, which were originally used in mean field dynamo theory, for example. More advanced methods, for example, those which Dmitry Sokolov was developing with Zeldovich and Molchanov and Druzmaykin, which are more sophisticated. They show directly that mean field dynamo theory does not need scale separation. So it's worth having it in mind, because scale separation rarely occurs in reality. For example, this is an example of simulations of local simulations of interstellar medium driven by supernovae, multi-phase interstellar medium. They are simulations of Fred Gent, very recent ones. So here, both mean field and fluctuation dynamos are at work. These are segments of magnetic lines, and some arrows give the direction. Similar, not exactly the same simulations, but similar ones. They show that this is a Fourier spectrum, power spectrum of the total magnetic field. You don't see any minima that you might expect from if the scales are separated. One maximum at large scale, small wave number k, another maximum at large k. No, you don't have any signs of scale separation. But if you look more carefully at this, and we did it with both Fred and James Hollins, if you smooth this field with a scale of about the scale of the turbulence, 50 to 100 parsecs, then you see that the large scale field, the result of such averaging, filtering, Gaussian filtering, has a scale much larger than the scale of the small scale field. So this is the spectrum of variable in space, mean field, averaged field, and this is the spectrum of the small scale field. And their spectra differ strongly. So there is some scale separation, but it's hidden. It's not immediately clear if it's present. Still, in these simulations the other week, the scales of the small scale field and large scale field differ only by, say, a factor of 3 or 4. So, no scale separation. How you define mean quantities, how you average, over what scale you average. And then, as I said before, there's a whole range of various ways to average. But what people do in theory, ensemble averaging, which is impossible in simulations because it requires millions to get a good convergence in ensemble averaging, you need millions of realizations. In simulations, you have at least at most handful of them. In observations, we have only one single realization to observe. So ensemble averaging is only good in theory. In various simulations, people use various volume special averages. But this is not what is done in observations and extensive simulations, DNS, for example. There, the mean quantities are observed by Gaussian or top hat smoothing. The telescope beam does for you that, and you can then smooth it further to get the averaged field. And then the mean field will be a function of time and position. Time if you have simulation, position if you have observations. And then these averages used in observation and simulations, they approximate the ensemble averaging only under weight scale separation, which is not there. But what's the implication? For filtering, the Reynolds rules of averaging do not apply, unlike ensemble or these other averages. The consequences can be quite strong. Here again, what I show is the same simulation of Fredgent, of local region in the interstellar medium. And then this is the mean field obtained by Gaussian smoothing with some suitably chosen scale. This is the mean field. It depends on position. It's not uniform at all, even across this relatively small box of 1 kiloparsec across. And this is a random field. Now, a widespread method to average in such cases is horizontal averages. If you so you take a plane at constant z, xy plane, and you just average magnetic field in that plane. Of course, what you get is that uniform magnetic field at given z. Very different one. Very different fields. They have different energies. And what is especially important, they depend on time differently. This is the similar simulation, dependence on time of magnetic field squared at various scales. So this is the total field, how the total field grows because of the dynamo action in this simulation. Now, if you use a horizontal average, the mean field will grow like this. If you use Gaussian smoothing, the growth is different. The growth rates, the slopes of these two curves are very different. If you will try to compare your simulation with a dynamo model or any other model, this can destroy your comparison. Different averaging methods give you different growth rates. Of course, this applies also to the random field, to fluctuations. There also, if the large-scale mean fields show different growth rates, likewise, the small-scale fields also show different growth rates. And here the problem is how to select this averaging scale. In observations, it is first telescope beam, which averages the image you observe for you, and then you can apply further averaging. At what scale? What scale separates the mean and field and fluctuations? Well, obviously, there is a turbulent correlation scale, but the mean field can have a scale twice as large or 3 times as large or half. How to choose L? And this is an open question. I don't know the answer. What we tried to do with Fred Gent and then with James Hollins was we were selecting the averaging scale to maximize the difference in the scales of the mean and the fluctuating fields. I'm not quite happy about this because it's ad hoc approach, ad hoc criterion, but I think we should think about it. How you define the mean field? What is the averaging scale given that the scale separation is not there? It's an open question to me. I don't know the answer. And I hope that this meeting will bring us maybe a bit closer, at least, to think more about this question, to find the acceptable answers to this question. Then, what are the consequences of using this filtering approach to get the mean fields? The consequences can be quite profound, and it's important to appreciate them. For example, for ensemble or statistical averaging, the Reynolds rules apply. If you take the mean quantity, which is not fluctuating, multiply it by fluctuations and average, the result will be the product of the two, and the mean of the average will be equal to 0. if you apply ensemble averaging twice, if you average again the average quantity, then it will not be affected. Averaging twice doesn't change the quantity. The result is that, for example, the square of magnetic field average, then the energy density of the total field will be equal to the energy density of the mean field plus the energy density of fluctuations. Excellent. It's not that easy with the Gaussian smoothing by telescope beam or with hand. For example, with Gaussian smoothing, if you apply this smoothing twice, still there will be change. So you have your image, you smooth it with Gaussian kernel once, you have a smoother picture, less coarse-grained. You smooth it again with the same kernel, the same scale, picture will change. Moreover, the mean value of fluctuations that's observed is not equal to 0, and the square of the total field will not be equal to the sum of the squares of the mean field and fluctuations. So, in one of the papers which you submitted, where we were discussing these problems, the referee comment was quite striking. It was that since the Reynolds rules of averaging don't apply, this method of averaging is useless and the paper is useless. But this is what telescopes do for you. In fact, there is a well-developed formalism how to use Gaussian smoothing or any other filtering, Fourier filtering or sliding averages in real life. It was first developed in large eddy simulations of turbulence. And there is a whole range of papers which explain how this can be done mathematically rigorously and physically meaningfully. I will not, these are references. I have no time to discuss it. It's the subject of a separate talk. So what's the message of this part?
2 minutes left.
Sorry?
2 minutes left.
Yeah. So be careful. We should be aware that what telescope does for us, or our final resolution does for us, they distort our assumption that Reynolds rules are satisfied. And for example, that the total energy is equal to the energies of the mean field of fluctuations. No, this is not the case. We have to be careful. So then, very quickly, evidence of dynamic action. First, there is to claim that you have a dynamic action in your simulations, we have to satisfy the necessary conditions for dynamos. For example, for the rotation dynamo, Reynolds number must be larger than the critical value, as discussed by Kando, of the order of 100, in fact, much more. But in simulation, the resolution of delta, Reynolds number cannot be larger than the ratio of turbulent scale over resolution squared. This means that to get Reynolds number larger than, say, 100, resolution should be better than 10 parsecs. Not many simulations which claim that they have fluctuation dynamo do have a resolution that high. This applies to a disk. For example, in circumgalactic medium, where L naught can be of the order of 1 kiloparsec. Obviously, the required resolution will be of the order of 100 parsecs. Still, very restrictive. So when we claim that we observe fluctuation dynamo in our simulations, we have to first demonstrate that the Reynolds number in our simulations is large enough. How to estimate the Reynolds number in complex simulations? You can always do that. You can always do that. For example, we did it with James Hollins using the autocorrelation function of magnetic field, say, or velocity field which we did with James. So at small separations, the correlation function can be approximated by parabola, which allows you to define the Taylor macroscale, lambda, which is directly related to the Reynolds number in your simulation. So this is what we did in our simulation of local interstellar medium. This is the autocorrelation function in small separations. And in that simulation, we have the resolution of 4 parsecs. And the correlation scale of the fluctuations of velocity was 60 parsecs. So from the previous slide, the maximum Reynolds number we could have was 200. In fact, when we calculated the curvature of the autocorrelation function at the origin for small x, we obtained the estimate of the Reynolds number of 20. And again, the referee said that this means that our simulations are substandard. No, they are not substandard. It's just that other people don't do that. Very often, especially in simulations with various artificial numerical viscosities and diffusivities, it's difficult to estimate Reynolds number. No, you always can do this to estimate your effective Reynolds number in your simulations. I think that there should be a standard that any simulation should report the effective Reynolds number, magnetic and kinetic, in those simulations. Otherwise, it's very difficult to interpret them. Amit Setter was using estimate of Reynolds number, which is good for direct numerical simulations, where there's the explicit and the only dissipation mechanism, for example, ohmic diffusion in this case. Can also be done. You can always find how to solve a problem. For mean field dynamos, large Reynolds numbers are not necessary, but the dynamo number can be large, should be large enough, as Tango again said. And the dynamo number, the value in your simulation, is sensitive to the amount of stratification, the scale height of the disk. So to capture the mean field dynamo action, the disk thickness needs to be very well resolved. Otherwise, it's difficult to claim the presence of mean field dynamos. Then, temporal special structures. Especially important and difficult this problem is. In the case of magnetic fields in galaxy formation, in forming galaxies, in collapsing gas clouds. There, in a collapsing gas cloud, exponential growth of magnetic field is not necessarily a sign of dynamo action because of the compression. Pakmore and Springle, I really like that paper. They suggested to transform MHD equations to commute coordinates of collapsing gas cloud. And then what needs to be done now is to redo basically most dynamo models in these commuting coordinates. For example, and then we can see, I can expect that the evidence of dynamo action will be a super exponential growth of magnetic field rather than simply exponential. Sharanya-Sur with Christoph Federak suggested to look at the growth of magnetic field over order of power 2/3 frozen in magnetic field under spherical symmetric collapse as evidence of dynamo action. This is a step forward, but not enough, because this remains constant without dynamo action only for the magnetic field along the axis of a, say, rotating cloud. But velocity share differential rotation can enhance this ratio above a constant without any dynamo action. Even frozen in field can have this ratio larger if there is differential rotation in a collapsing cloud. So what are do we have any unique signatures of the fluctuation dynamo? I'm not aware of them. But what is promising, what I find very interesting, there was a paper of Galeva, Dmitry Sokolov, and Sasha Rozmaikin in 1989, where they considered the correlation tensor of magnetic field directions. This is exactly what observations, for example, for starlight polarization give you, or far infrared polarization. You don't have only orientations of magnetic field can be used here. And they showed, moreover, what is important is that this tensor unit vector, here are the unit vectors of magnetic field. They are sensitive to both regions of strong and weak magnetic field. They are not biased, this quantity isn't biased towards the region of the strong magnetic field. And then this paper shows that this tensor has two characteristic parts. One behaves like a cosine of a stretched radial distance, another as a sine. Fantastic. These two parts of this correlator, they have very distinct and characteristic behavior. Power of Rm enters here, this logarithm. this to me, nobody has ever applied it to any observations. I would think that this is a sort of a treasure trove. We need to try such things. We need to find other signatures of fluctuation in mean field dynamo, which are robust and reliable. So my conclusions are quite, I don't shy from making them provocative. So analysis of either simulation observations is difficult, and it requires much more care than we can often see. And then we still have to find convincing and robust signatures of either fluctuation or mean field dynamo in complex environments. We need to find them, and I'm pleased to see that many speakers in this meeting are also concerned about this problem. I really think it's one of the important steps towards better understanding of dynamo action in galaxies. So, as Kandu mentioned, this is the cover of our book to be published in December. Many questions which I discussed and Kandu discussed are discussed here. The book is good, I'm telling you, but extremely expensive, £165. So think twice before wasting your own money on it. Thank you.
Thank you very much, Anwar, for a very nice talk. And now we can take one question. We're kind of short on time, and then we have to go to the discussion.
So Rainer please go ahead.
Yeah, thank you, Anwar, for this very instructive talk as usual. So I'm very pleased to hear that this scale separation is not needed anymore. That was always my feeling, that the small scale and large scale dynamo are not two different worlds, so they must be connected somehow. So can we go as far to say that there is no physical transition between the two, and that there is a continuous transition from small to large scale? That means, does the large scale dynamo have a whole spectrum of modes which leads into the smaller scales? Is that thinkable? I asked that already to Luke, and he also said, yes, it's maybe possible, you may remember. So would you agree that this is a possibility which should be investigated in future?
Yes, Rainer, absolutely agree with you. I will share my screen again to show you one slide which just shows exactly that. Can you see my screen?
Yes.
So look at this. This dashed line is the spectrum, power spectrum of the mean field. This line, dotted line, is the power spectrum of the fluctuating field. They overlap. At this scale, for example, this scale, there is both some of fluctuations and bit of mean field. At this scale, there is a less of mean field and more fluctuations, but they are completely mixed. I completely agree with you, Rainer. I completely agree with you, with what you say.
Thank you.
Okay, thank you. And I think there are more hands, and I think the thing we should maybe do now is just continue answering the raised hands, but now it will lead into a general discussion about all of the presentations so far.
Yeah, so now you can unmute yourself and please feel free to discuss.
If possible, I would like to say that situation with identification of small-scale dynamos is much easier in solar dynamo studies because there we can observe temporal evolution of magnetic field in a particular body, and there I don't say that it is an easy undertaking to isolate traces of small-scale dynamo action, but still statistics of sunspot number during solar minima do show that the contribution of small-scale magnetic field. I think that after reasonable efforts, that ideas can be how to say rescaled to comparison of amplitudes of small scale magnetic fields in arm and interarm region, it is reasonable to try. Thank you very much.
Thank you, Dimitri. And next question. Next, I think it was it Fred?
Fred. Yeah, Fred, please.
Yeah, I'd just like to comment on this discussion between Rainer and Anvar about the separation of scales between the mean and the random field. When looking at the spectra that Anvar was showing, we are really talking there about the separation of scales between the fields as the observed or as the seen. But there is it's not the same necessarily as the separation scales between the dynamo mechanisms, because clearly as you grow the small scale field with the through small scale dynamo, that then is acted on by the large scale dynamo, which will turn some of that small scale field into large structures. So, and it's hard to separate the two fields in terms of the behavior and the pattern. So when you look at that overlap, you also have the opposite, is that the small scale field will be turning some of the large scale field into random field through small scale turbulent action. So you do get this overlap of the spectra. But what I would argue is that it's probably, I would still think, the case that there are the scales that create those two different fields are acting on different scales. So there's much large scale fields which drive the formation of a large scale field, and it's mixed up with the small scale dynamo, and there are much smaller scale structures which lead to the formation of a small scale field, and it pulls some of the large scale field into it. So that's where the overlap comes. But if you look at the actual forces, the direction which creates those two elements, well, yes, they are separated, and it's not necessarily clear how they are separated, what scales are separated on, but I think we need to understand more about the dynamo mechanism. That doesn't help with Rainer's question as far as observation is concerned, of course, because I think when it comes to the observation, it will just be a continuous spectrum. It's very difficult to decide how to or where to separate the two. But perhaps if we understand the mechanism which creates them, we have a better clue as to where we should place the separation.
May I ask a follow-up question?
Yes, please go ahead.
Yeah, Fred, very interesting. Could you make a plot from your models of the amplitude of the dynamo modes, or make something like a Fourier analysis of the spectrum? So that is something we can provide from observation, so that we can know how much to expect for higher dynamo modes. I remember very old plots from, I think, Anvar's previous book, showing the first three modes and the amplitudes would significantly decrease. So can that be increased to, I don't know, in future observations, you may be able to distinguish between up to say 5 modes if we are very optimistic.
Okay, I think that's something that needs to be done on a full data set. So in terms of the older runs from which Anvar was talking about, we didn't really capture enough subsets, some data sets, in order to do that kind of breakdown of the sets. And it's quite complicated as well to determine what scales to look at, particularly if you want to use this volume averaging, which I think might be more physically informative than the horizontal averaging. Now, if you do the horizontal averaging, you can do that on the fly. But if you want to look at the more complex structure of a mean field and use kernel smoothing to define your mean field, then that's much harder to do on the fly. Well, yes, I think it's worth doing, and with the newer runs, we will be able to capture much more data. We have much more storage capacity, and I think it'll be useful to produce such an analysis, which will vary over time, because as the fields grow, we need to understand which modes are actually growing fastest. So that hasn't been done, but we can do it, and we will do.
Yeah. So next is Kandu. Kandu, please unmute yourself.
Well, I thought Anvar was there, but anyway, I just wanted to just elaborate or emphasize a bit more what Dimitri was saying, because I've been thinking a little bit about this, that we have not looked so much at time correlators. We have looked a lot at spatial smoothing and spatial correlation. So it could be interesting that, I mean, of course, one knows that the final state of, let's say, alpha squared periodic box thing is one big sine wave, which is there forever. So that's obviously correlated on very long time scales, whereas the small scale field in some sense will be correlated on some eddy turnover time scale. There may be no scale separation even there, but we have not explored it as much as spatial correlations. And this could be probably useful in simulations to try because different K modes may have different correlation times also, whether they have. So I don't even know the answer, but I think this also builds on what Dimitri was saying, that there in the sun's case, you have 11-year cycle. But then if you're thinking about small scale fields, they may not last for as long as 11 years. So there's a clear scale separation in time. And maybe there would be something to look at further in numerical simulations also. But of course, I agree with Anwar that, yeah, we have sorted out all our difficulties in the book, so we agree. Thanks.
Yeah, thanks. Anwar, sorry for missing you initially. Please go ahead. You're muted.
No problem. First about this, what Kandu said about time averages, about time correlations to distinguish fluctuation from large-scale dynamos. No, it's good because in the sun, the example which was provided by Dmitry is that the large-scale field has very clear time signature, 22 years cycle. In galaxies, it's not the case. We don't expect the large-scale field to be oscillating in time. So what we need is a signature which is unique to, say, fluctuation dynamo, which, for example, frozen-in magnetic field will not have. And I think that in galaxies where there is a tangling of the large-scale field by turbulence, you will have the correlation time equal to the correlation, comparable to the correlation time of turbulence in the small-scale field, but it will not be a sign of fluctuation dynamo. So the problem is to find those features of magnetic field produced by the fluctuation dynamo, which cannot be produced without dynamo action. For example, with a frozen-in magnetic field. Or, next step further in complexity, not frozen-in magnetic field, no dynamo action, non-ideal MHD. How you decide if you have fluctuation dynamo? Exponential growth is not sufficient. K to the power 3/2 sort of Kazantsev spectrum is not sufficient because magnetic field will always have spectrum will have peak at smallest scale, that is in linear stage. So what I could, from the results available, I could only find this very unusual correlator of the magnetic field directions, unit magnetic fields, from the paper of Galeeva, Dmitry, and Rusmakin. Honestly, I couldn't find anything similar in uniqueness. Again, uniqueness, I'm not sure what will happen with this correlator if there is no dynamo. It's unexplored area. And second, also we need to rederive dynamo solutions, at least simple ones, even simpler ones haven't been rederived, in co-moving coordinates of a collapsing gas cloud. My expectation is that the signature of the dynamo will be a super exponential Lagrangian growth of magnetic field, not simply exponential. But it's only my speculation. I simply don't know. We need to do that. Thank you.
Yeah, agreed, Anwar. Next is Axel. Axel, please go ahead.
I have a question which connects observers on the one hand and some of the global modelers that we will have later in the afternoon. What is the current status on distinguishing between primordial origin of galactic magnetic fields from a dynamo one in terms of the axisymmetric spiral and obtained by measuring RM around a circle around the galaxy versus bisymmetric spirals what is the situation? This is a question mainly to Rainer at this point, but Rainer may have already seen comparisons with global recent simulations.
So may I reply to Axel? Axel, this is a very old question raised many decades ago, and I think this is not actual anymore. I think no simulation at all, I don't remember anyone says that the shape and the strength, the pattern of the primordial field plays any role for the final distribution of the dynamo. So that just doesn't, the galaxy doesn't care. It just needs some primordial weak field and that's it. And what the pattern is. And the old idea that the primordial field will develop into a bisymmetric one, I think that was just wrong. I think it's unphysical. It will not work. And by the way, there is not a single dominating a bisymmetric field in galaxies at all. So the old claim by Marita Krause that has been proven to be incorrect by work with Andrew Fletcher, unfortunately not yet published. So there's not from observation any indication, and also from theory no indication that the pattern of the primordial field plays any role. So I think we should just disregard this question at all.
Okay, since Rüdiger Packmore has a screen on, the question then, is it easy to make a symmetric spiral feature from the RM measurement around the circulus from purely primordial magnetic fields without dynamo action, or with just injection from star forming regions?
So we have looked at so it really depends. So in the end, the question is well, there are still limitations in comparing these things in the end, right? But so what we have done in the recent version from a paper by Enrico Garaldi this year, we have looked at the same cosmological Milky Way-like galaxy with very different seeding mechanisms. So one of them was run with the cosmological uniform field at very small values that we usually do. Then there were two that had seeding some high redshift, with at reionization and such, and one that was essentially a supernova seeding. So only when there are stars they see magnetic fields. And essentially the properties of the magnetic field in the galaxies are indistinguishable by any statistics that we looked at.
So it would be good enough to explain the observations, you think, in terms of large scale fields?
As good as and as bad as any of the models we have do it. Essentially, the turbulent dynamo combined with the in and out flows from the galaxy, always erases any kind of knowledge about where this magnetic field initially comes from in our simulations.
Yeah. So the only problem is that the strength of that large scale field may still be insufficient.
So I think that's also a problem. So I think or not. So it really depends on which level you're looking at. I think so. To 0th order, we clearly get the good large scale magnetic field strength. So and I think Rainer showed this in the plots, the typical strengths of the ordered azimuthal component of the magnetic field is several 10 microgauss or so, which is completely consistent with what you observe. The one thing that we don't get, and there I think it will be interesting to see to which degree this is a shortcoming of the simulations, or whether there might potentially be some biases in the interpretation of the observations, is that we don't get a large scale coherent field in radial and vertical direction, at least close to this, right? So these fields, as Rainer has shown, live on typically KPC scales for us. But one of the things that we have looked, for example, when we tried to see what kind of Faraday signal that would give, then one of the also clear results in our simulations is that the Faraday signal is not and does not depend on the global magnetic field of the galaxy, but really is completely dominated by the local bubble of a few KPC around the observer, because both the electron density and the magnetic field strength decline exponentially with distance. And then because they have like exponential profiles internally, and then there's just like the signal is just very local. So like essentially it doesn't depend on what happens on the other side of the galaxy.
Thank you. Yes,
but yeah,
very interesting.
Remains to be seen.
I just wanted to mention that there is a pre-recorded talk that does address this question of primordial magnetic fields and what signature they might have in nearby galaxies. So if you have a look at, and that person could also comment if they want to.
Yeah,
So
next,
Rainer.
Yeah,
ask Rüdiger. So that is something which worried me always, that in your models there are no global coherent fields. So what is your explanation? What is the reason? So do you include any large-scale dynamo action, or is that not yet included? And if not, what would be the prospects to get these global coherent fields in your models?
Okay, so there's one important point to make, is that we do not make any assumptions on any dynamos whatsoever, right? We're solving the full ideal MHD equations, and there's no approximation in there that limits us to like see a specific dynamo or to not see a specific type of dynamo. The main limitation that's crucial is, or the two main limitations that are crucial, and I mentioned discussing very briefly now, I can like save the time later. The two main limitations are resolution. Like, so the like in the really the full cosmological galaxies, we get down to like a few 10 parsec or so, right? Like, which is like maybe very insufficient for some of the things. And the second one is the description of all the various feedback baryonic physics things, right? So like, how is energy input into the ISM by exploding stars, by a million other things, right? And so by like modeling of cosmic rays, whatnot, right? Like there's lots of things that we only understand very poorly, and that has a significant effect on these things. And so this may change what kind of thing happens to the magnetic field. But fundamentally, the magnetic field is evolved with the full induction equation, and so it has the full back reaction on the velocities. And so whatever the velocity field is and how it evolves in the gas will eventually set what the magnetic field is.
Thank you.
I think Sergio wanted to say something.
Yeah, just commenting again. So you mentioned my work. There's a recorded talk on this. So one of the questions I always been interested is, we have these limits from Planck, right, on the strength of the primordial field, and it seems too strong to me. So one of like the pre-recorded talk is based on using this method where we do a simulation similar to what Rüdiger usually does, but we separate the field into two channels and we follow them separately. And we try an extremely strong primordial field, or what I think is extremely strong primordial field. And by looking at the field separately, we actually find that we can distinguish the two in the galaxy. That is not to say that they have different signatures, although I hope that that is the case. But again, we are trying fields that are much higher than those that Rüdiger uses. But we do indeed find that the fields are separable in terms of their properties, primordial and supernova injected. Just
a very brief comment about this. This is a whole different discussion. So I would strongly argue that the lower limit on the intergalactic magnetic field paper by now has been completely ruled out, or like kind of it has been shown that this paper is incorrect.
You mean the
and so
lower,
this limit
lower...
doesn't, the Neronov one.
Okay, yeah, but I meant the Planck limit. So that, yeah, that's
oh yeah, the Planck, yeah. So like it can be arbitrarily small, right? But it will not be on the large end, very likely. So yeah, like if you make it high enough, I think you can have an effect. And I think we have seen this a little bit in the past, like Federico Marinacci tried this a while ago.
Exactly, yeah. So I was inspired by that work where he finds that the number density of galaxies is reduced, right? So I really think if primordial fields are strong, we should be able to use galaxies to tell whether they are strong, but just rule them out. So I think we should work more on that.
No, I think also, I watched your talk. I think the results are essentially completely consistent with like what we've seen, at least like from order of magnitude, right? So that like if you go for a 10 to the minus 20 field, you wouldn't see anything. But if you go 10 to the minus 12, 10 to minus 10 of this order, then you actually see a difference.
So just my last comment then on the whole thing is that my whole feeling is Planck is 10 to the minus 9. I think galaxies could give us around 10 to the minus 12. Again, that is very numerically dependent on my simulations, but because I personally believe, I was convinced when I started my PhD that magnetic fields, primordial magnetic fields should be weak. But yeah.
Okay,
Thanks.
I think
Next.
there are a couple of hands raised, so let's continue the discussion for a few minutes, but then we should really, we're getting into the break time now, the lunch time, so we should probably end in a few minutes. So go ahead, you can unmute whoever's.
Yeah, so Kandu and then Anwar. So Kandu, please unmute yourself.
Okay, I'm just a very brief comment that, I mean, since I've looked at primordial magnetic fields also forever, that the Planck one is an upper, as Rudiger said, is a limit, so field can be arbitrarily lower. But the place to look for primordial fields is not in structures, I think. It is in the voids and away from structures, because that's where it will not be affected by all the structure formation stuff that's going on. So I think it's still worth doing gamma ray observations, gravitational wave studies, or whatever else that you are thinking about, and not necessarily look for it in galaxies. And galaxies, I agree. I didn't catch what was the limit which Sergio mentioned, 10 to the minus 12 or something you said? Or?
Yeah, that would be sort of my order of magnitude guess. Yeah.
Okay, that's quite believable, I think, and yeah, that's a very small comment I have to make.
Thanks, Kandu. So Anwar, you are next, please.
Yep. Rudiger, did you try to, in your simulations, to calculate the mean helicity of your flows at various scales, just to see if the helicity, if the flow is helical enough naturally in your simulations, becomes helical enough to drive mean field dynamo. So what is the dynamo number in your simulations at various scales? Obviously, the value of this helicity will depend on the scale on which you average, so it should be a scale dependent quantity. First, and second, just in connection with primordial fields, if indeed there are galactic dynamos working, then galactic dynamo creates an eigenfunction, and what we observe is an amplified eigenfunction of the dynamo equations, which will make absolutely irrelevant, as Rudiger says, what was the initial field. So trying to see the traces of primordial field initial conditions in the observed galactic magnetic fields, I think are hopeless. What we see is non-linearly distorted eigenfunction of the dynamo equations, rather than any distorted primordial field. But more importantly, Rudiger, have you tried to measure this mean helicity of random flows in your simulations?
Yep, so the simple answer is no, which is partly because this is like a very hard to compute quantity in these kinds of simulations, because it's like we don't have the vector field, and so like computing the helicity is actually tricky. You can probably try other things that are similar-ish, but I haven't done this.
He means the kinetic helicity. So you need just a curve.
Yes, I mean kinetic helicity. You have velocity, take its curl, you multiply them together, you average. What's difficult?
No, you're not talking about a magnetic helicity.
No.
No, I'm
okay, and as kinetic, I can do.
Kinetic helicity. Is
it?
This
I can do.
Yeah, it's large enough to drive mean field dynamo, or is it not?
Yeah, this I can easily figure out, but I haven't tried this yet. One of the things I can, or like about the whole scale separation from a simulation point of view, from these like cosmological simulations, is that so we have at some point tried to like look also more in detail on velocities at different scales and so on. And so in the velocity, so there's two things. So first, in the simulations we are running with the resolution we have, there is no separation of scales in the velocity field, which I think is makes it very hard to get a separation in scales in the magnetic field. This is so essentially like I've tried various averaging things and so on, and whatever you average, you're always dominated by the scales that are just close to these things. And so, however, these simulations are limited because in like physically there are potentially two scales, right? So like the one like there's one scale of kind of the whole galaxy, and accretion of gas on this galaxy and the differential rotation in this galaxy live on that scale. So this is like for Milky Way, this is like a few 10 kpc. However, there's a second scale, and that is the injection of energy from individual supernovae. And like as large as supernova remnants get before they become part of the smooth ISM. And this is somewhere between 10 and 100 parsec or so. Now, none of the cosmological simulations resolve properly, right? So this scale is like usually massively smoothed over if it's properly there at all. So there's some chance that this kind of the injection on small scales of supernova energy and the injection of accretion and energy and the differential rotation give you a feature in the kinetic power spectrum. This is however, this is a completely non-trivial statement that adding these two together, you actually get a local minimum. So, but I think there's a chance that something like this will be the case, but it would be very interesting to have any like observational or better observational constraints as this on this as well, if possible, like to really like see if there is a feature in edges on a certain scale.
And the first talk of this session is by Suyan Mao, which is about probing interstellar magnetic fields with the SK. Anne, please.
Yeah, thank you very much, Luke and Amit, for organizing this special workshop. It's good to see everyone, even via Zoom. And thanks for giving me the homework to do to talk about what we expect to achieve with the rich polarization data from the SKA in terms of galactic magnetism science. So here I will just select several topics to cover. I'm sorry and apologize if I haven't covered your favorite topic, but for the time interest, I will only mention several interesting topics on the magnetic fields in the Milky Way, nearby galaxies, and in distant galaxies in terms of the prospects for the square kilometer array. So for those of you who are not familiar with the SKA will be hosted at 2 different sites. SKN1 Mid will be located in the Karoo's in South Africa. It will contain 133 15-meter dishes and 64 13.5-meter meerkat dishes with a maximum baseline of 150 kilometers. And here are the frequency coverage. And in terms of frequency deployment, band 2, 1, and 5 will be deployed first, and then eventually we'll get frequency coverage from 350 all the way to 24 gigahertz. Meanwhile, there's also SKA1 Low, which will be located in Western Australia. It will cover the frequency range from 50 to 350 megahertz with 130,000 log period antennas across 65 kilometers. So for the deployment specifications of the SKA1, please refer to this publication here. And key science project observations are expected to commence late 2029. And for details of the SKA timeline, you can check out this website here. And if you're interested in joining the SKA Magnetism Science Working Group, please contact the co-chairs. So much of what we know about magnetic fields in the universe comes from radio polarization observations. 2 key observables, polarized synchrotron emission from the object of interest itself, and rotation measure grid, which is a collection of Faraday rotation of background polarized sources to probe magnetic fields in the foreground medium. And Faraday rotation is given by the line of sight magnetic field weighted by thermal electron densities. And the sign of the rotation measure tells you the direction of the magnetic field along the line of sight. So you can tell the coherency of the magnetic field from these RM measurements. So our understanding of the rotation measure sky really have evolved since the early 2000s, when we only had few rotation measures across the entire sky. Now, thanks to the NVSS rotation measure catalog and the Southern SPAS compact array catalog, we have about 1 rotation measure per square degree in the sky. And with the square kilometer array 1 era, we hope to get up to 2.6 million extragalactic sources in the entire sky. So one major development that's very important in our field in the past years is the advent of broadband radio polarimetry. We can now get gigahertz of bandwidth with very fine spectral resolution. And we can now get polarization properties and Faraday rotations without ambiguities and very precise measurements. And now we can employ a new set of analysis tools to characterize the magnetic fields, densities, and turbulence in the ISM that was not possible before using just narrowband data. I have to mention that the origin and evolution of cosmic magnetic fields have been one of the key science drivers for the square kilometer array. And for the latest magnetism science case for the SKA, please refer to this publication by the Magnetism Science Working Group published last year. And there were also 7 chapters on ISM magnetic fields in the SKA science book back in 2015 that you may be interested in. So I put the link here as well. So while we are all very excited about the prospects of the SKA, most of us are now being kept busy by the polarization surveys being carried out with SKA precursors and pathfinders. So this is not an exhaustive list, but I just want to show you that there's a lot of activities going on that would already produce very exciting science before the SKA era. And also we have to keep in mind that there's also possibility of the NGVLA coming online. So here's the brief outline of the science topics that I would like to cover today. I will first begin with the Milky Way and then talk about prospects of SKA with nearby galaxies and distant galaxy science. So based on the current set of observables that we have, people have come up with more than a dozen different models for the large-scale magnetic field in the Milky Way. So Tess Jeff wrote a very nice review summarizing these models back in 2019. And there are some common features from these models. For the disk magnetic field of the Milky Way, we know that there's at least one large-scale magnetic field reversal along the Sagittarius arm where the field points counterclockwise as opposed to towards the outer galaxy where the field points clockwise. Also, if we look at the symmetry of the disk magnetic field across the midplane of our galaxy, most of the part of the galaxy, the magnetic field does not reverse, disk magnetic field does not reverse direction across midplane. So there's even parity is preferred. On the other hand, the halo magnetic field is much less well constrained. Here's an example of a halo field model from the Jensen and Farad 2012 model. So the SKA and the Pathfinder era will give us substantial improvements in various galactic magnetic field traces. First of all, we will go from the all-sky rotation measure grid of 1 source per square degree to initially few tens of Faraday rotation measures towards background sources with POSSUM and the MPIFR galactic plane survey, and eventually go to a density of around 90 sources per square degree for the SKA1 mid all-sky rotation measure survey. And this rotation measure grid, this denser rotation measure grid will also be a broadband rotation measure grid covering at least 900 megahertz of bandwidth. So with this denser broadband rotation measure grid, we're bound to uncover more new features about the galactic magnetic field. And we're actually already doing this with smaller studies. So please see Shanahan's talk on Thor's rotation measure, extreme rotation measure discoveries towards galactic quadrant 1. And also Jackie Ma's work on showing that towards galactic quadrant 1, the galactic magnetic field is not symmetric across the midplane. The SKA is also expected to detect all the pulsar population in the galaxy. So for SKA phase 1, about 10,000 pulsars will be discovered. And the increased number of pulsars means that we will get also a larger fraction of pulsars with Faraday rotation measure. This number is now only 1,300 pulsars with rotation measure, but it could go to a few times higher than what we have now. And importantly, these pulsars will also have independent distance measurement, which will help us to better model the electron density distribution of our galaxy from the DMs. And so it will eventually help us to better locate, for example, the exact number and the location of magnetic field reversals in our Milky Way. It has also been shown recently, I think it's a very important point, is that from synchrotron emission and diffuse polarized synchrotron emission maps, we can start to distinguish polarization signatures that are produced by local features versus those produced by a genuine large-scale global magnetic field. So SKA pathfinders and the SKA will have surveys that will provide maps of these diffuse polarized emission of these foreground objects. And it will help us to better characterize them and try to remove their effects from for example, the all-sky rotation measure grid before modeling the large-scale magnetic field of the Milky Way. And there will also be traces, new traces for the galactic magnetic field in the coming, with actually already now and with the SKA even more. So this includes, for example, fast radio bursts, which provides both rotation measure and dispersion measures. And this calls for new algorithms and new inference algorithms to infer both the electron density distribution and magnetic fields of the Milky Way. So please see these talks at this conference for details. So with these set of improved, significantly improved magnetic field observables from the SKA and its pathfinders, we hope to be able to characterize much better the strength and the structure of the disk and the halo magnetic field of the Milky Way in order to do direct comparison to theoretical predictions. So one possible method to trace the global magnetic field structure of the Milky Way that really hasn't been receiving much attention is the possibility of using Zeeman splitting of OH masers towards star-forming regions in our galactic plane, and use the sign of the magnetic field that obtained from this Zeeman splitting to trace the global large-scale magnetic field. So from Zeeman splitting, you get a sign of the magnetic field, which tells you the direction of the magnetic field along the line of sight. And it's a in situ magnetic field measurement. So you're not dealing with complicated sightline integrals as you do in Faraday rotation towards pulsars or extragalactic sources. And also with the spectral information, you can get some kinematic distance estimate. So essentially putting like a small compass at the location of the star forming region in the galactic disk at a certain distance. So people try to look for the connection between the global large scale field and the directions of the magnetic fields indicated by Zeeman splitting of OH masers done already back in the 1970s. Right now we have compiled of about 200, accumulated about 200 Zeeman measurements towards star-forming regions in the galactic plane of our own Milky Way. So I've made this plot from these various studies here. It's color-coded such that the red points here means a positive Zeeman measurement, which means that the field is pointing away from you. And the blue points here are negative Zeeman measurement, which means that the fields are pointing towards you. So you can kind of see that there's an indication that the direction of the Zeeman splitting seems to be towards these star-forming regions seems to be patchy. There seem to be some kind of organizations on parsec scales. But what's very fascinating and intriguing is the result from the MagMode survey, which looked at Zeeman splitting towards star-forming regions along the Carina arm. And what they found is that nearly all the Zeeman measurements along the Carina arm indicates a magnetic field pointing away from you. And this is actually the exact opposite direction in which the magnetic fields were inferred from the Faraday rotation towards pulsars and extragalactic sources in this direction. So very intriguing result. So right now we only have around 200 of these Zeeman measurements in the galactic plane, and it's very difficult for us to say anything statistically significant in terms of any possible alignment with the large scale field of the Milky Way. So we need larger sample size. And a deep blind survey for OH masers on the galactic plane with the SKA and its pathfinders will be able to do that. So on the short term, the gas cap OH will be able to provide such measurements, increased number of Zeeman detections towards star-forming regions in our own Milky Way. And we'll be able to compare field directions with other tracers and establish any connections, if there is any, between the Zeeman magnetic field directions and the overall global field of the Milky Way. And if so, understand why and how best to include them in modeling the large scale magnetic field. So now moving to really the smallest scale magnetic field. Another topic that I would like to briefly touch upon is measuring the small scale magnetized turbulence. So we know very little about the magnetic power spectrum on small scales. And the regular tracer, the normal tracer that we use to probe magnetic power spectrum will be what I call the static rotation measure grid, where you construct structure function using the background rotation measures of extragalactic radio sources. And this morning we heard from starlight polarization, we also will be able to get the magnetic power spectrum on these scales. But the static rotation measure grid really doesn't get you down to sub-parsec scales. What we can take advantage of is monitoring pulsar rotation measure and dispersion measure time variabilities. So we take advantage of the fact that pulsars move in the ISM relative to the Earth. And so our line of sight towards the pulsar actually changes over time. And it samples basically different part of the turbulent or patchy interstellar medium. And by monitoring how the dispersion measure and rotation measure changes over time and doing correlation analysis and knowing the distance to the pulsar, we can actually probe the magnetic power spectrum down to sub-parsec scales. So people have done this kind of work on dispersion measure time variability, and they've shown that the electron density fluctuation on sub-parsec scales follow Kolmogorov spectrum. The good thing about doing simultaneous RM and DM time series analysis is that one will be able to disentangle the magnetic fluctuations from the electron density fluctuation and really reveal the true underlying magnetic power spectrum on these scales. So currently, there have been already a lot of effort to do this kind of work by monitoring hundreds of pulsars with LOFAR for the past 7+ years, and continuing this kind of effort for longer time with LOFAR, and eventually with SKA1 low on a large number of pulsars to be discovered with the SKA, can really expand on the number of sightlines that we probe and also on the scale size that we probe, because the longer that we monitor these pulsars, the larger scale, physical scale we can go to, and we can join up with the spectrum inferred from static rotation measure grid and starlight polarization. And on the other hand, if we can better measure Faraday rotation, both in terms of the frequency coverage and also better ionospheric rotation measure modeling, we can improve the sensitivity to the actual astrophysical rotation measure variation, so probing down even to smaller scales. So hopefully with the SKA and these kind of monitoring effort, we will know much better about the magnetic power spectrum on various scales. So now moving out of the Milky Way, I would like to say a few words about magnetic fields in nearby galaxies and what the SKA will be able to help us to understand. So we already heard from fantastic talk by Rainer this morning about magnetic fields in nearby galaxies. So here I attempt to summarize in just a few words. So the two main observables for magnetic fields in nearby galaxies are again polarized synchrotron emission, and we have that towards about 100 galaxies. And we have the rotation measure grid towards about 3 galaxies that have large enough angular extent to have enough background sources to do this experiment on. And I must refer you to Rainer and Richard Rybinski's review in 2013. Rainer actually takes great effort to update this paper periodically and quite regularly. So please look up his reference. And the latest update was 2021, and he continuously adds new galaxies that have polarization observations and magnetic field measurements into this paper. So our current knowledge, general knowledge about magnetic fields in nearby galaxies are only based on a dozen galaxies with the best available data from which one can derive reliable magnetic field properties. So again, please see Rainer's talk this morning for details, and Rainer and Luke's detailed review from last year for the details of our current knowledge, and also Marita Krau's papers on the halo magnetic field. So regarding the disk magnetic field, we know that there is a coherent component on kiloparsec scales, and the coherent component has a field strength of about 1.7 microgauss. This is the median value from the dozen galaxies from which these measurements were possible. We found that S-symmetric modes seem to be dominant, and reversals seem to be rare. And also, if you look at the parity of the magnetic field across midplane, the even parity is preferred. So these properties are broadly consistent with the general dynamo predictions. But as you already heard this morning from Rainer's talk, there are still many details and many phenomena that are not understood at all. So regarding the halo magnetic field, the total field strength is about 5 to 10 microgauss, and we oftentimes see these X-shaped magnetic field patterns, and their origin is much less well understood than the disk field. So we know that by measuring polarization from a polarized emission from a galaxy at different wavelengths, it allows us to do magnetic field tomography. A classic example of that would be the work by Andrew Fletcher et al. On M51, where he had used narrowband polarization data at several discrete frequencies, 3, 6, 18, and 20 centimeter, and taking advantage of Faraday depolarization effect. So if you effectively look through different layers of a galaxy at different wavelengths, at short wavelengths, 3 and 6 centimeter, because you're less susceptible to Faraday depolarization effect, you effectively look through the entire galaxy, whereas at longer wavelengths, because of the lambda square dependence of Faraday effect, you are more susceptible to Faraday depolarization, and you can only look through the top layers of this galaxy. So taking advantage of this, he was able to decompose the observed polarization across these wavelengths into a disk magnetic field and a halo magnetic field. And now with even broader band coverage of the polarization measurement of M51 and other galaxies, we can start to fit the observed polarization as a function of frequency to various magneto-ionic medium model for the galaxy. So we want to do this for more galaxies, but only a few galaxies have broadband polarization data. One of the notable survey with broadband polarization coverage was the changes survey, but even with that, there were large frequency gaps. So frequency coverage is often not complete. So what we hope to do with the SKA is to conduct a magnetic field census of a large sample of nearby galaxies by mapping the polarized synchrotron emission from these galaxies across wide frequency range. So we plan to make use of band 2, 3, and 4. So going from centimeter, 20, 30 centimeter out to around 5 centimeter wavelength. The high frequency end of the observation is needed because we want the highest spatial resolution to combat beam depolarization effect. And the highest frequency end will also mean that you have negligible Faraday depolarization, so you can properly measure the properties of magnetic fields in the disk of galaxies where it's very turbulent. On the other hand, the lower frequency end of the proposed SKA observations is needed to conduct tomography and model the Faraday depolarization due to both large and small scale magnetic field structures. And what would be very exciting with the SKA is that it will have enough surface brightness sensitivity to map these polarized emission at extremely high angular resolution. So at least 10 times better than what we have now. So still keeping about a physical resolution of 100 parsec for galaxies at a distance of 14 megaparsecs. So this will allow us to, for some of the galaxy, maybe resolve out some of the turbulence in these galaxies and really combating the beam depolarization effect. And from these set of observations, will also provide us with a rotation measure grid of extragalactic sources behind the galaxy to probe through the magnetic field integrated along the line of sight through the entire galaxy. So a joint analysis between the rotation measure from background extragalactic sources and that from the diffuse emission will hopefully reveal reliably the three-dimensional field of magnetic fields in nearby galaxies. So what we—
And sorry, it's 22 minutes. So
okay, I will have two more slides.
Yeah.
Okay, I will wrap up quickly. Yeah, so so hopefully we'll get a much better handle on both the disk and halo magnetic field strength and structure. As Rainer said, we will have the sensitivity and resolution to look for higher dynamo modes. From these depolarization analysis and measurement, we'll be able to understand more about the nature on the random magnetic fields, the isotropy and anisotropy of these fields. we'll search for large-scale magnetic field reversals in these external galaxies properly and understand their origin, and it will facilitate also a better comparison with magnetic fields from other tracers, such as that from the SOFIA far-infrared polarization observations on nearby galaxies. So please see these talks by the SOFIA Legacy team. And for each of these galaxies, then what we need theoretically would be individualized theoretical predictions of magnetic fields based on the individual galaxy properties. So very quickly, 1 minute, I will just talk about the prospect of SKA to measure magnetic fields in distant galaxies. I won't go into the details here, but using gravitational lensing system, so background polarized source lensed by foreground galaxy, can allow us to cleanly isolate Faraday rotation produced in the lensing galaxy, and therefore clean measurement of the magnetic field strength and structure in individual distant galaxies. And we've already shown from a paper in 2017 that we can measure magnetic fields in distant galaxies now using this method. Particularly, we found that this galaxy at redshift of 0.44 has microgauss magnetic field with isosymmetric magnetic field being the preferred field geometry. And we can directly put a limit on the amplification timescale of galactic magnetic fields. So for results of the full sample, please stay tuned for the papers coming out by my PhD student, Tamir Kovic. So currently we are limited by the number of systems for which we can apply this method to. But with the SKA, we are expected to discover more than 10 to the 4 new gravitational lensing systems. So there will be many more systems that are suitable for these kind of magnetic field studies. And if we combine the result from the magnetic fields traced by these lensing effect on distant galaxies with other distant galaxy magnetic field tracers, such as deep observations of integrated polarization properties of star-forming galaxies, as well as a combination with theoretical predictions, so like the work done by Luis Rodriguez and Luc Chemandi, we'll much better understand how galactic magnetic fields grow over cosmic time in the SKA Pathfinder and the SKA era. So I won't say much more, but here's a summary of all the science topics that I've covered, our current knowledge, and what SKA and Pathfinders will bring us. I'm sure we will come up with more observations and observational details we get. I think the more questions will come up, and so that we can continue to work in this field for many more years to come. So thank you very much for your attention, and apologies for running slightly over time.
Yeah, thanks, Anne. Are people with questions, please raise your hand. I see Rainer. Rainer, can you please go ahead?
Hi, Anne. So thanks for this very nice overview. I have one remark and one question. So the remark refers to the OH masers. Yeah. These are embedded in spiral arms and they trace very small scales. So that's not a surprise that the difference to RMs is there, because there you trace mostly the turbulent field within the spiral arm. So I'm not surprised at all. This is different from the integrated RMs from pulsars. Would you agree, or?
The interesting part is that the line of sight component along that arm from the maser measurements seem to be all directed away from us. If it's scrambled, if there are some positive and some negative, then yes, that's not so surprising. But I think there's, of course, in order for this method to work, the cloud has to have memory of the ambient large-scale field. It has to somehow preserve the direction of the large-scale field when it collapses. And I think under some conditions, it may work, but I think we need to investigate this more, maybe look into simulations, whether or not this is actually possible.
Thank you. A very brief question. So you mentioned the need for band 4 of the SKA,
yeah,
which is the S band. And with the JVLA, but in the beginning you did not mention band 4, so it seems not to be part of SKA1, right?
So the current deployment scheme is that band 2, band 1, and band 5 will go first, and then the other bands will come as upgrades. So my hope is that eventually we will get these bands as well.
Okay, thank you.
Yeah. Any other questions? I don't see any hands up. There is a discussion going on in Slack. Sorry, Anwar. Anwar has his hand up, please.
Thank you. If I can, these X shapes in the galactic halos.
Yeah.
Isn't it just a generic configuration of a large-scale poloidal field in almost any reasonable magnetic configuration in the disk, especially if there is an outflow which will stretch magnetic field in the poloidal direction? So it would be strange if the structure of the poloidal field was different from that. So it's not a problem of explaining them. They're natural, aren't they?
No, Anwar, sorry, I disagree, if I may.
Sure.
I mean, the end, was a question.
No, go ahead, fine. Rainer, go ahead.
No, Anwar, the X shaped means that the vertical field component becomes stronger with increasing radius, and the poloidal field expects the opposite. So I think it's not consistent with poloidal fields. The poloidal field.
But why? Why you think that? What you say expected? Expected from what?
From
the strength of the poloidal field depends on the strength of the outflow.
Right, but the outflow then must be stronger in the outer parts, which is not.
I don't know. It's a structure of the outflow. The velocity ratio, not velocity itself. Velocity shear that matters.
Okay, agree. Yeah. Okay. Thank you.
Yeah, but connecting to that point, I think there is kind of a disconnect between the edge-on galaxy population and the face-on galaxy population. People who study edge-on galaxies versus people who study face-on galaxies. A galaxy seems an edge-on galaxy. If we turn it face-on, what would the signature of the X-shaped field be in the polarization observations? I think that's something we need to investigate.
Okay, yeah, I think we can also move this discussion to Slack, and there is some discussion on Slack also. Can you please take a note? Next, Axel, please share your screen. Yes. Yeah, okay. So the next talk is by Axel Brandenburg about expected observational signatures from galactic dynamo simulations. And Axel, I'll switch on my video after 18 minutes and give you a 22 minutes notice. Okay, please take away. Thank you.
Thank you very much, Amit, and thanks to the organizers for inviting me to this presentation. I was asked to talk about the expected observational signatures of galactic dynamos from simulations. And there's a number of aspects that have crossed my mind in recent years. A lot has to do with magnetic helicity fluxes and helicity reversals. That's one of the aspects I will talk about. There is also the question of large versus small scales. We heard a lot today about the spatial, about scale separation, and I will comment on that aspect as well. In all cases, I will keep an eye on what are potential prospects of observing various features, in particular with regard to the magnetic helicity. There is Faraday depolarization or cancellation of it. There's also the B-mode polarization, another interesting aspect that has not received sufficient attention yet. But regarding small scales, it is important to talk about the observational signatures of ionized versus neutral components, and I will also show a spectra on that. Magnetic helicity is in a very important quantity in magnetohydrodynamics and in astrophysics in general. It is because it is structurally a very different animal than any of the other quantities. So magnetic energy, for example, receives energy by doing work against it, against the Lorentz force, and is being dissipated. There's no such sourcing in the magnetic helicity equation. And that is one of the reasons why it plays such an important role. In particular, you cannot generate it just like that. If you were to, it corresponds to such a topological interlocked flux ring. If you were to generate it by tilting a loop, as is here done, in fact, even quantitatively, what you do is you do not generate any net helicity, but you do generate helicity at different length scales. You produce it at small length scales first, but only at the price of also doing at large scales, or even the other way around. You produce it at large length scales according to the Parker Parker loop of lifting something by buoyancy and letting it expand because of the decreasing density. But this comes at the price of producing inevitably small-scale magnetic helicity. And that strikes back, as Kando was already explaining in his talk. This really all has to do with the magnetic helicity conservation equation if magnetic fluxes are absent. In particular, in that case, what is known as catastrophic quenching corresponds to a strange behavior in the late saturation phase of a dynamo. And so here's shown time normalized by in turbulent diffusive time units. You have initially an exponential growth, which doesn't look linear because it's a double logarithmic plot here. But you see nicely that the large scale magnetic field in red is always subdominant, not by much, but by a sufficient amount with respect to the small scale magnetic field. And that is something that is unacceptable in order to explain the large-scale magnetic arms of our galaxy. So we must get away out of this. If we don't have magnetic helicity fluxes, it takes a really long time to build up the large-scale magnetic field by waiting for the small-scale magnetic helicity to be dissipated. And that goes only at a resistive time scale. Here's shown what we call a vacuum cleaner experiment. If you remove by a Fourier transformation artificially the small length scales, you see that the large-scale magnetic field immediately continues to rise and is no longer subject to this magnetic helicity constraint. Magnetic helicity fluxes can be measured and have been measured. And here is a result from Fabio Del Soro and company, which shows very clearly that at moderate magnetic Reynolds numbers Rm, below 1,000, the small scale magnetic current density term, which of course would be absent if you really had an ideal simulation. And under such a condition, by the way, no dynamo can actually exist. Dynamos must have small-scale magnetic diffusivity. If they do have that, and if you know exactly what they are, you will find that they are at first comparable to the electromotive force term, which plays a role for producing the large-scale magnetic field. And ideally, you would like to lose the small-scale current helicity through these fluxes. And so what you find, however, is that in this evolution equation, the small scale, the magnetic helicity fluxes are always subdominant. The flux divergence is shown down here, and it becomes potentially comparable only at the very largest resolution. And this is a simulation of now 8 years ago, but it has recently reproduced in a very different context by François Rinson, who calculated, and this is a picture of his work, which assumes magnetic helicity fluxes through the equatorial plane. And again, he finds similar color coding, that the magnetic helicity flux divergence is small, but it does become comparable, and here even more convincingly so, to the large scales. And this is then the key under which we hope to alleviate catastrophic quenching. Magnetic helicity fluxes must be explained. What is the mechanism of driving them? There has been a lot of literature on this. One of them is the so-called Wishniak and Cho flux. Over the years, and at least since 2012 with the paper with Hubbard, we have shown that this term cannot actually explain the numerical simulations. What we think instead is going on is that the small-scale magnetic helicity flux is being transported by a negative gradient of the small-scale magnetic helicity density times some diffusion coefficient, the turbulent diffusion coefficient. So in this case, small-scale turbulent diffusion does play a role, but only for the fluxes, not for the other quantities. Now, the curious thing is, in order to carry negative flux out of a simulation, because here we have the dynamo domain as here's the height in arbitrary units. Here's the external halo, which could also be that of a stellar corona, for example. We need to get rid of negative magnetic helicity. Negative magnetic helicity. In order to do that, we need to have a positive gradient of it. And so this leads inevitably to a sign reversal of the magnetic helicity at some distance above the dynamo domain. Here's one simulation, an early one, which showed that in the context of a mean field simulation, that we have seen similar behaviors by comparing observationally for the sun, both in the solar wind using in situ simulations and at the surface, where you can, in both cases, calculate helicity spectra. So here is shown the helicity spectrum multiplied by K, which is always beneath the energy spectrum shown in dotted lines, and the different colors give the sign. Here applicable to the southern hemisphere, and we see that there's a sign reversal at one particular scale. This scale, after expanding out into the solar wind, corresponds to this scale, and we see a complete disparity between what is at the surface and what is in the wind. The sign has reversed. And this is, in fact, similar to what has been seen in stellar simulations of a corona, negative in the domain at the surface or positive in the southern hemisphere, like here, but it becomes negative, blue, in the halo. Does this also apply to the galaxy? In order to measure this, we need to think about new observational techniques. One of them is from this paper with Rodion Stepanov, which involves the cancellation of Faraday depolarization. If you have Faraday rotation, you sum up for sufficiently long wavelengths the contributions from all the different angles due to the Faraday rotation. That gives you zero effect for sufficiently long length scales. However, in the presence of helicity, helicity also leads to a rotation of the perpendicular magnetic field component, and that can cancel the effect of depolarization. And that means that instead of having peaks around zero for zero wavelengths, then you would have maximum transmission, you can shift the transmission peaks to finite lambdas, wavelengths. And so here is shown such a plot, and we expect different signatures in all the four, or in pairwise different quadrants of the galaxy. Here we see an edge-on galaxy. That's the sketch only. No such measurements have been done, but we hope that this can be done in future by measuring the Faraday depolarization effects in the northern and southern hemispheres on the left side of the rotation axis and compare this with the right side of the rotation axis. And we should see a crosswise correspondence where only in diagonally located quadrants we see maximum polarized intensity. Another measure is the E and B polarization, which also comes just from Q and U, but Q and U are coordinate system dependent quantities, as it has long been known to cosmologists. They used to decompose the polarization Q and I times U, I as imaginary unit, into what is called the E and B polarizations. This can be done locally, like with Fourier transform, or globally using spin-2 circle harmonic functions. You get two classes of fields. E is a field that looks the same if you look at it in a mirror. A ring remains a ring, a cross remains a cross. These are two different sides of E polarization. And here's B polarization. And this is a spiraling pattern. If you look at this in a mirror, it actually does not remain, it's the same. It actually becomes that of the corresponding negative B polarization. So this is something like parity violation that we see here, which must have its origin in something. Does it have its origin in the alpha effect? In fact, in the paper together with Marcus Bruggen, and also I forgot to write down here, we have shown that the bipolarization alone shows such a pattern where there is opposite signs north and south. However, if you average longitudinally, there's a lot of cancellation, negative here, positive here. And yet there is a net value which is positive in the northern hemisphere, negative in the southern hemisphere. Where does this hemispheric dependence come from? Does this perhaps come from the alpha effect? In order to answer this question, we have looked at various dynamo models. And by comparing, what we have done is we have decomposed this. We have looked at the expansion coefficients here, and the mode with circular harmonic M corresponds, of course, to the azimuthal average. So that is shown in the first part of the table, which I will concentrate on here. And we find a negative value from a mean field dynamo model, which is comparable to the observations in two different polarization bands, the Q and the K band. One is dust emission, one has to do with synchrotron emission. So in order to explain this negative sign, we have run various models. We can in fact even change the model, change the alpha effect in this model. And we do find a change of different signs, but the nature of the dynamo becomes so completely different unless you also change at the same time the differential rotation. If you change also the differential rotation, then what we see is that the sign does actually change. And so the change, and we have even the same values. And so the change in the value really has its origin in the sense of the spiral. Remember, the bipolarization is sensitive to patterns on the sky that look like a spiral. It could come from something like what we could call a cyclone in the stellar context, or an anticyclone, but it could also be just from the viewing angle of the spiral of the galactic spiral. If you imagine looking at this from the inside, it looks different north and south if you look north and south. There's another interesting aspect which has to do with this clover leaf picture in the bipolarization, and that can actually be simply explained in terms of a preference of vertical magnetic fields locally as opposed to horizontal magnetic fields. This leads in both cases to a clover-like pattern, but to have the bipolarization positive in the first quadrant, you need to have a mostly vertical magnetic field. That's the origin of this particular pattern. Regarding large and small length scales, let me make the following comments. If you have narrow scale separation, it is straightforward, since for a long time in dynamo theory, to not treat the alpha effect as a multiplication with the mean magnetic field, but as a convolution. In practice, however, this has never been done in reality. And only recently have we come across a way of modeling this by including non-locality in terms of an evolution equation for the mean electromotive force. If you neglect time derivative and spatial derivatives, you have the usual EMF in terms of alpha and turbulent diffusion tensors. But if there's temporal non-locality or spatial one, you can fix that. And that leads to completely different new aspects. It can even lead to new dynamo effects. Not that those are necessarily an explanation for the galactic dynamo, but they do play a role. In particular, temporal memory effects have been studied in a paper with our chairman, Luc Chamandi. But there's also other aspects to small scale dynamics. In particular, if you really look at the evolution equations for the ionized and neutral separately, you see, especially in the regime of large magnetic Prandtl numbers, that the magnetic field, first of all, has an extended energy spectrum, all the way from the energy carrying length scale here at this smaller wave number K to higher wave numbers. And then it falls off, but the kinetic energy falls off very, very rapidly. But this is only true for the ionized component, for the neutral component, and not for the ionized component. The ionized component does actually, even though it may not have much of a density, its velocity, however, is dramatically different and more comparable to what it was at smaller wave numbers. You see here particular features in the ionized component, which are not present in the neutral component, and whether those observable will need to be seen in future. And there's another aspect, namely that if you look at the E and B polarizations differently, the E polarization, which is the parity even one, so it has nothing to do now with helicity or handedness, it shows a remarkable skewness, and it also shows a kurtosis. And this kurtosis is particularly large when the medium is sufficiently weakly ionized. In all those cases, the skewness and the kurtosis of the E polarization is remarkably strong. And so it is important new diagnostics that we should all look at in future, namely to do the EMB polarization, not so much because of the galactic spiral or because of the alpha effect, but because of another way of diagnosing something at the small length scales, which are otherwise not that directly detectable. My last aspect has to do with efficient versus inefficient dynamos, in particular the dissipation. And this is an aspect that has to do with the fact that the magnetic Prandtl number in galaxies is very, very small. Sorry, very, very large. So what is shown here is a standard diagram of a dynamo. A dynamo consists of magnetic energy, and it gets its energy from kinetic energy, nothing else. And this kinetic energy gets its energy in a model from four sinks, and in both cases, it's being dissipated either viscously or ohmically, Joule heating. So it's important to measure viscous versus Joule heating, and both have different signatures. I will not go into these, but this would be an important aspect for the discussion. So if the dynamo is efficient, which we do expect, then a lot of energy should go from kinetic into magnetic energy. So the magnetic energy should be large, but also the dissipation should be large. And this is actually not the case in simulations. In simulations where you actually have access to the magnetic Prandtl number, this means you must not do an ideal simulation where you have 0 divided by 0, but you must have something where you have a large viscosity divided by a small diffusivity. One aspect, of course, is the fact that real galactic media are are collisionless, and the concept of viscosity really is modified. And this is another open aspect, what that really means. So how is it to be explained? If on the one hand, we expect the dynamo to be efficient and yet inefficient in the sense of not being able to dissipate anything. The answer comes in terms of two different length scales. The efficiency is only true at large length scales, where a lot of kinetic energy at large length scales, LS, is being converted into magnetic fields. But then at smaller length scales, and it doesn't need to be very, very small, it is being converted back into kinetic energy, and that is being dissipated. It's not being dissipated resistively, but it's actually viscously dissipated. How can we measure this, diagnose this? We can do this by doing a spectrum of the work done against the Lorentz force. So you Fourier transform the Lorentz force, you dot with the velocity in Fourier space, and you obtain a spectrum. And the larger the magnetic Prandtl number is, the larger should be the length scale, or the smaller the wave number at which you see a sign change in this work term, which indicates at which length scale does this conversion swap. We call this the reversed dynamo. So with this, I have covered various aspects. And in particular, what is important to realize is that the north-south difference in the bipolarization, we believe, comes from the galactic spiral and not from the alpha effect. Helicity, magnetic helicity in the halo is an important quantity which we need to understand. It may be possible to determine this with Faraday depolarization, a big tool for the future. And finally, looking at the kurtosis and skewness of E and B polarizations is perhaps the most promising way of learning something new about the small length scales that are otherwise not directly accessible to us. Thank you very much.
Thank you, Axel. Thanks a lot. So are there any questions for Axel? Please raise your hand.
Hi, Axel, that was very comprehensive and very interesting. This kurtosis and skewness, you presented it as a result of the simulation, but why is that? Why is it a probe of the small scale? I mean, it went a bit fast. Can you just?
Yes, it is not really a probe of the dynamo aspect as such, but it's a probe of the physics on the one hand, of small length scales, and it's a probe of the degree of ionization. It's a new aspect that we have seen, and which, of course, itself needs to be understood better.
Right.
And maybe it even does carry other information which we are not aware of. So at the moment, it is a new tool, and we have tried to understand it, and we have seen interesting applications in terms of learning other things about the interstellar medium, not necessarily about the dynamo.
Okay, so this is in your paper with
2019 paper in Monthly Notices.
Okay, I'll have a look and get back.
Thank you.
Thanks. Next is Anwar. Anwar, please go ahead.
Axel, with this, what you are saying about E and B polarization as measures which are applicable in the whole sky rather than the local patch like Stokes parameters, right? Indeed true, and my comment is a question, in fact, to observers, to Anmao, to Mareike, to Rainer. When you discuss, for example, we saw today maps of the whole sky, for example, infrared polarization, Planck data. These are data of the whole sky. Shouldn't you use the language of E and B polarizations instead of Q and U? What do you think, Axel? And then I wonder what observers think about it.
So I think there could be so it doesn't need to be only at large length scales. So for example, for the cosmic background radiation, it has to been analyzed in overall length scales, and the spectrum has been analyzed. I could imagine diagnosing locally with bipolarization is still a hemispheric dependence from something like an alpha effect, but then only at intermediate length scales. I wouldn't call it necessarily small length scales, because if you have a cyclone in the sky, a cyclone has itself a certain orientation with respect to gravity. And so we could directly determine the handedness of the cyclone, whether it really is a cyclone or perhaps an anticyclone, by looking at bipolarization. So that the difference between looking at bipolarization or the origin of bipolarization from helicity versus other effects has to do with the fact whether there's a physical mechanism that can actually swap the plane into an opposite case, into a reversed plane. If you have isotropic homogeneous magnetic helicity, any plane looks the same from any viewing angle. But this is not the case if you look at a cyclone, because the cyclone has a definite thing of what is up and what is down. So I actually think there is hope in that. So far, I have not been successful in that, or haven't done it sufficiently.
Thanks. Next hand up is Kandu.
Sorry, I'm coming again, but Axel, what I understand from you is that since you're sitting inside the galaxy, you're not able to make out the alpha effect using the bipolarization antisymmetry, right?
Yes, at the large length scales. And that was a question of Anwar's, where I'm hypothesizing that at small length scales, it could well be different. We have tried it actually for the sun, but unfortunately, even there, we haven't been successful yet observationally. But that doesn't mean that that it doesn't work. From simulations, actually, we know it does actually work. So there could be a signature.
So my question was, would you then advocate looking, for example, at edge-on galaxies where you see everything from outside the galaxy, and both the north and south hemispheres?
Yes. So again, at large length scales, edge-on galaxies we've looked at do show a lot of signature that are all parity invariant, but then none of them that we have looked at so far really have to do with the helicity. And so again, I I mean, it's important that somebody looked at this, of course. So this has now been done, but it's also true that is not the end of the story. There could be interesting aspects still at smaller length scales, which we need to double check.
Have you also, sorry, looked at the EB cross correlations?
Yes, so I find actually that looking at B polarization is a much more telling aspect rather than the cross correlations. Both of them can be done, and I found it actually a real novel aspect that somebody did it first for just the B polarization, because we would want to look at hemispheric dependencies and especially at certain features. Whether you can extract those aspects and also from the correlations needs to be then seen, of course.
Yeah, okay.
But originally, of course, I started with E times B polarization, as all the other people were doing. And then I realized, oh, there's much more of a story to be told if you actually look just at B.
Okay, fine.
Axel, sorry. In my comments, I really hoped that in your response, you will tell observers, do look at E and B polarizations. Stop looking at Q and U alone. But you are too polite to say that. Therefore, I'm saying that for you.
Yeah, you're absolutely right, Anwar. Of course, it's stupid to look at Q and U because that's not a good quantity to look at. And of course, in cosmology, everybody has known this for 20 years since the work of Seljak and others, of course.
But Axel, this is hard for us. You see, we are living in the Q and U world since decades. So to get used to the E and B, it is not easy, and that needs help. And I just want to say there's an enormous database now from the Changes survey. Edge-on, there are more than 20 edge-on galaxies. And these could be evaluated in this way, but due to the lack of man and woman power, I think there's clearly somebody needed who takes care of that. I think the Q and U maps are maybe available, I'm not sure. So there's really something to look into that. Do you have already access to this data?
I mean, of course, we looked at WMAP data, and Planck is another source, of course.
No, this is low.
And there's also old data. That is right.
No, this is very high resolution data of the order of
yes. Okay. So if you have access to this, I'd be happy to look at those data.
Well, you have to. I would suggest to contact Ralf-Jürgen Detmar because he's in the steering committee of the Changes.
Yeah.
And also Michael Stein, who may be online, he is working on Changes data. So the Bochum group is clearly the one who are best suited, and they have also access to all the data. So please contact them.
There's a reference in the chat from Marika.
Yeah. So
there's a question, but Marika,
there are few hands up still, but I think in interest of time, can we please, I apologize, please move this discussion to the Slack. So the next talk is by Rüdiger Packmar, who will talk about cosmological simulations. And Rüdiger, at 18 minutes, I will start my video and then tell you at 22 minutes again. Thanks. Please.
Okay, then thanks to the organizers for organizing this very nice meeting, and also for giving me the opportunity to talk here. The organizers asked me to discuss one point specifically, and that is the effect of magnetic fields in cosmological simulations, or what actually changes in the cosmological simulation when we include magnetic fields. And so since this is already quite, there are already quite a number of interesting aspects, I will really concentrate only on this point in this talk and not talk about the things we discussed very briefly before in the discussion anymore. That is what magnetic fields we actually get in detail and how to compare them to observations or so. If you're more interested in this, I'm still around all day, so I'm happy to discuss this and you can send me questions, but the focus of this talk will really be on the effects of magnetic fields on galaxies in cosmological simulation. Okay, just to set the stage, let's briefly let me briefly say a few words about cosmological simulations in general. So what we do is we run cosmological simulations so that typically means a significant chunk of the universe in a periodic box that is of order 100 megaparsec large or so. And then there are two types. Either we have we distribute the resolution reasonably uniformly in space. These are typical cosmological box simulations like illustrious TNG, or we throw all our resolution elements on a single galaxy. That's that's then called a zoom simulation, and then we really resolve one galaxy in beautiful detail. There's what the galaxy there's a lot of like physical processes that we need to implement there. Lots of like baryonic physics, how gas cools, collapses, forms stars, how the stars then eject mass and energy back into the interstellar medium, how black holes evolve and produce feedback, and so on. And the only thing I will say about this really here is that like by now we actually have a reasonably good understanding of the model, and as we have shown in like dozens of papers, we can reproduce with the model that we use in Auriga and illustrious TNG. We can reproduce the observed galaxy population reasonably well in its global properties, but also in like lots of properties of like sizes or their like time evolution, things like this. For the magnetic fields, we simulate magnetic fields completely self-consistently by solving the ideal MHD equations. So there's no, again, just to repeat this, there's no approximation that would limit us to any specific dynamo processes. We start with a small uniform seed field in these simulations. Typically, small means like of order 10 to the minus 14 Gauss or so. Because it's ideal MHD, we need to put some magnetic field in. So there's no process that generates a magnetic field out of nothing. But we have like tried different seeding models by now. In the latest version by Enrico Garaldi from this year. And for the magnetic fields in galaxies and around galaxies, it seems to not matter what we exactly do with the seeding. And again, as I just said, like there are lots of processes. So it doesn't matter what we do with the seeding, and that's mostly because at high redshift there's an efficient turbulent small-scale dynamo that amplifies the magnetic field over many orders of magnitude until it saturates at some fraction of the turbulent energy density, and then this erases any memory of the seed field, and then the magnetic field evolves on to, as far as we can tell, realistic strength and probably other properties at redshift 0. But I will also not go into the detailed comparisons here. One important limitation of all of these cosmological simulations is the resolution, and that's important to keep in mind. It's like essentially the conservative estimate of how far down you can trust the simulations is about 100 parsec or so. There are cells in the simulation that are significantly smaller, but the processes there and also the number of cells that are smaller essentially mean that we cannot properly resolve the smaller scales. So in particular, we don't have any individual molecular clouds in there, which is important to keep in mind. Okay, I will hopefully in the remaining 15 minutes cover briefly 4 different parts. First, the dynamical effects of the magnetic field on disk galaxies, the effects of the magnetic fields on the circumgalactic medium in our simulations, the effect that magnetic fields have via cosmic rays, and Zweibe will for sure go into much more detail about this directly after me. And then one of the things that we learned, and that's quite interesting in illustrious TNG that we don't have fully understood, is like the effect on the AGN model. Okay, let's just start from kind of the oldest, in a way, of our results from 2017. And so that was the first big sample, big meaning, I think it was 20 galaxies, Milky Way-like galaxies in cosmologic assumed simulations that we ran fully self-consistently with magnetic fields. And then 4 of them we also ran without magnetic fields to get an idea of what the magnetic field does to the galaxies. And so what's shown here is the star formation history of those 4 galaxies. In black, I think it was with magnetic fields and in red without, but it doesn't really matter because the lines are essentially identical. And so the important point here is that the star formation history, so when does the galaxy actually make stars and how much, is a quite sensitive measure of the dynamical history of the gas in the galaxy and of the evolution of the galaxy as a whole. And so despite the magnetic field, as we see in a second, being in equipartition with thermal and turbulent energy at redshift 0, it doesn't have any significant systematic effect on the total amount of stars in the galaxy or when they form in those galaxies. So then the question is, why is that if the magnetic pressure should be relevant at redshift 0? And the main 0th order explanation for this is that in our simulations, we reach a true equipartition too late for the magnetic field to really have a strong effect. And so what you see here is the evolution of magnetic, turbulent, total kinetic, and thermal energy in the disk at a distance from the center of about 10 kpc, so somewhere in the middle of the disk. And what you see is that you get like this really fast exponential amplification at high redshift, but then this exponential amplification essentially saturates at about 10–20% of the turbulent energy, as you expect this for a turbulent small scale dynamo. And then it takes a long time for the magnetic field to amplify, to be amplified further until it reaches equipartition with thermal and turbulent energy. And only then it's dynamically relevant, but that by that time, most of the stars have already been formed, right? Like, so at like a few gigayears before redshift 0, at redshift after 0.5, then not much happens to these like disks galaxies anymore. And so this general statement that like there's no huge effect of including the magnetic field on the global properties of galaxies, I would argue still holds. Although we will now look into like lots of like different properties and details and other ways where this statement might change in the future. So the first thing where this is not really true anymore, or where we see an interesting difference, is described in a paper from Joe Whittingham, who is a PhD student in Potsdam from this year. And what you see here are 4 galaxies. Again, zoom galaxies at similar resolution to the one I showed before. This is also at redshift 0, and in the top row, you see simulations with magnetic fields, and in the bottom row, you see the identical simulations without magnetic fields. And so what you see here is just a stellar light. And so you can immediately see that there is a systematic difference in those galaxies. And the difference is that the disks with magnetic fields are systematically larger than the disks without magnetic fields. The total stellar mass is still very similar, so with kind of the same within the noise, but there is a significant structural difference between those galaxies. So one question is like, what's actually different in those galaxies than in the ones I showed you before? And the main difference here is that those galaxies went, so the ones where you see a difference, went through a major merger a few gigayears ago, while the galaxies I showed you before were selected to have a reasonably quiet merger history. And so to understand why this makes such a big difference, let's just look at one example from this paper where you can see the gas evolution at the time of the merger and the evolution for the next 3 gigayears after this. And so you see on the top the gas density from a thin projection through the center of the disk to the midplane of the disk, and on the bottom you see the magnetic field strength. And you can see that in this like kind of very like, so this massive merger disrupts the existing gas disk, and you have a very violent, very energetic gas flow in the center of the merged object. And so under these conditions, if you have sufficient resolution, you can actually get a very fast, very efficient amplification, again by a turbulent small scale dynamo of the magnetic field. And so then this like strong magnetic field in the center becomes dynamically relevant for just a short time. and changes the properties of the gas in the center of the galaxy, and then has an by like this way also changes kind of the structural properties of the disk galaxy that then forms after this merger as the merger remnant. Okay, and yeah, I just recommend you, if you're interested to look into this paper, we go into like much more detail about how this exactly works and what exactly happens there. Now, if you look in, like, if you've seen this and know that the size of the galaxies is something to look out for, then you can actually also see this in some of the other galaxies, more isolated galaxies. So one of them is from a paper from Freke van der Voort from this year, where she looked at one of those galaxies. And so again, that we have looked at in the past. And so what you see here again is stellar light at redshift 0, with on the left without a magnetic field included, and on the right including the magnetic field. And also here you see a slight difference in the size of the galaxy. However, here this is the result of this is not does not come from from a massive merger. However, what's slightly different in those simulations is that Freke refined the circumgalactic medium quite a bit compared to the normal simulations, so that the gas around the galaxy is much better simulated at much higher resolution, so that we can model the processes of like kind of at the interface between the disk and the CGM, but also the inflows and outflows on the, like from the disk into the CGM and the cooling down on the disk and so on significantly better. And so if you look at the gas of this galaxy, so here you see in the top, so this is an edge-on projection, and in the top you see the magnetic field strength, and on the bottom you see the thermal energy over the thermal pressure over the magnetic pressure. And you see that there is some layer around the disk, like so just at this interface between disk and circumgalactic medium, where the magnetic pressure can become significantly stronger than the thermal pressure. Now, in this, and so kind of by having a magnetic pressure surrounding the disk that's dynamically relevant, what happens is that you can change the properties of the outflows or from the galaxy. You not directly not like how strong the outflows are, or if there are any at all, but you can change like the direction and the collimation and so on. And this is shown very nicely here, where she shows like several properties of the gas in the top row without magnetic fields and in the bottom row with the magnetic fields included. And so you can see that the main difference is if you look, for example, in the central column, you see that the pressure in the circumgalactic medium surrounding the galaxy, so this is on scales here of like several hundred kiloparsec, becomes significantly more smooth if you include magnetic fields. And you also, if you look at the radial velocities and the rightmost panel, you see that if you include the magnetic fields, the outflows from the disk become significantly more collimated, and so you obtain a much more stable kind of large-scale flow pattern in the halo, so that you really have this bipolar outflow, and then you accrete from the side. And so this is also, so essentially the inclusion of magnetic fields here changes these like large-scale flow properties in the halo. And this again then has a small effect on, but noticeable systematic effect on the properties of the disk. Okay. I don't have much more time left, so let's just briefly touch on the effect via cosmic rays. So we have heard this before very briefly already, and we will hear more about this like soon after me, that cosmic rays are one of the very interesting ingredients of galaxy formation that we just now have finally started to be able to include also in cosmological simulations. And there's two main important properties that are important here in the connection to magnetic fields. The first one is that cosmic rays generally, because they're charged particles, propagate along magnetic field lines. So the structure of the magnetic field matters. But it's not only the structure, it's also the strength of the magnetic field, because they are not only the speed of the propagation, but also how much energy they lose to radiation when they propagate and to thermal heating of the gas may depend on the strength of the magnetic field they're running through. And so what we show here is from a paper from Tobias book from this year, showing again, the same galaxy simulated with two different versions of a cosmic ray model. They both have anisotropic diffusion along magnetic field lines, but the one on the left also has an additional cooling term, Alfvén cooling, that we think is there in nature as well. But there's still, I guess, some like the details to be figured out from a plasma physics point of view. And so if we include this term, we get significantly larger galaxies than if we don't include this term. Now, why is this? The reason is, if you look at the reason you can see on the right here, so if you look at the cosmic ray and also on the cosmic ray pressure on the bottom, or the ratio of cosmic ray over thermal pressure on the top, then if we include this term, if we don't include this term, we get the pressure in the halo is completely dominated by the cosmic ray pressure. While when we include this term, then the cosmic rays lose a significant amount of their energy on the way into the halo, and so we are not dominated by the cosmic ray pressure in the halo. Now, why is the magnetic field so crucial here? So how large this effect is really depends on the strength of the background magnetic field, which is like not super well constrained from observations in the halo, for example. So as an example, if we compare our results with the FIRE collaboration that does similar simulations, then for them, this term is essentially irrelevant because their magnetic field in the galaxy is more than a factor of 10 smaller than in our galaxies. And so it really, like if you want to do cosmic ray physics well, it becomes really crucial that you have realistic, good magnetic fields in the galaxies, whatever that actually is, right? So unfortunately, no one can really take it. Okay, and then last but not least, like we also in illustrious TNG, which is in contrast to the simulation showed it before, is a box simulation. So we have a uniform resolution. So we have many galaxies that are equally well resolved in there. And so we can look at like properties of the population. And so what I like to focus you to focus on this plot is the black and the blue line. So this is for the method paper where we looked at like lots of variations of the model. And in particular, we looked at what happens if we only switch off magnetic fields. More specifically, we actually just set the seed field to 0 to make sure that all the numerics is actually the same with the Riemann solvers and so on. And so the black line is the fiducial model in illustrious TNG that we know agrees very well with observed galaxy properties. And the blue line is what happens when we switch off magnetic fields. And so one of the most interesting differences is that if you look in the top right panel, you see the black hole mass versus stellar mass. So the mass of the supermassive black hole in the center of the galaxy versus stellar mass of the galaxy. And you see that if we run without magnetic fields, we systematically get smaller black hole masses. That also means if you look at the top left panel where it shows the stellar mass over halo mass, that typically means, or that means that we have then less feedback if we run without magnetic fields, and so we get more stellar mass in the same halos when we don't include galaxies. And you can also see the gas fraction changes ever so slightly. The galaxy stellar mass function on the center left essentially doesn't change, and also the global star formation history of the universe changes only ever so slightly. Similar in the bottom right, the sizes of the galaxies essentially don't change. So that seems to be all within the noise. But because the AGN feedback, so the black hole feedback model can have such a strong effect on the properties of the galaxies. And by adding magnetic fields, you at the very minimum change the properties of the gas surrounding the black hole. So the total pressure there, the effective sound speed and so on, you actually have quite some lever arm to change the black hole feedback properties, and with that, the properties of the galaxies. Okay, and I just leave you with my summary to stay in time. Thank you.
Thanks, Rudiger. So that was very interesting. People, please raise your hand for questions. Anwar.
Thank you. Rudiger, just in the very beginning, you were showing this plots for the dependence on time of various energies, right? And I noticed that kinetic energy is sort of almost 2 orders of magnitude higher than thermal energy. This means highly supersonic motions. But what sort of kinetic energy is this? Is it large scale?
That's the rotation of the disk.
Yeah, but did you try to, this is exactly my question, did you try to separate?
Yes, so there was a poor attempt to define a turbulent energy in there as well. Let me quickly share this again. So the problem is there's also no good definition of turbulent energy, whatever this means, because it's like a continuous spectrum in these simulations, and wherever you cut, you immediately dominate. Wherever scale you cut, you like this, the energy on the smaller scales is immediately dominated by the larger scale. That's the
indeed.
I tried this a bit.
So yes, we have to do something right about it.
So the green line, so the red line, yeah, this is the total kinetic energy, and this is mostly in ordered rotation, so that doesn't really help you too much. The green line is an attempt of estimating a turbulent energy by taking by summing the radial and the vertical kinetic energy, and just assuming that this is all turbulent and the turbulent energy is isotropic. So this is probably a slight overestimate of the turbulent energy, but it gives you like an order of magnitude estimate, right? And so within this order of magnitude estimate, the turbulent energy, the kinetic energy, the turbulent, the magnetic, and the thermal energy actually are in equipartition.
Excellent, thank you.
One additional note on this: this is true in the disk. If you go to the center of the galaxy where there's no ordered rotation, the magnetic energy never approaches the turbulence. So it really stays at the saturation of the dynamo at like 10-20% or something. You need the ordered rotation to get to equipartition.
Thanks. The next question is by Ellen. Ellen, please go ahead.
So very, very nice talk. This is maybe a question that Axel wants to comment on too. So I assume that you have a star formation prescription in these simulations. So when gas is lost to star formation or gas is added due to a supernova, what do you assume about the magnetization that accompanies that? So do you lose magnetic field when you make a star, or do you gain magnetic field when you blow up a star? Can you say a little bit about how you treat it?
Yes, so this is actually a very good question, and this has changed actually over time slightly. But so the most important statement is it doesn't really matter for the total magnetic field what you do. What we do in the recent simulations is that when we make a star particle, then it eats up magnetic energy according to the mass that gets locked into the star. And when the star ejects mass, it comes without a magnetic field. What we have done in the past is we have models where we have played with models where we seed magnetic field from stars. That doesn't seem to make a big difference. And I've also run models a while ago, and the switch is still in a repo, that leaves the magnetic field as it is when you take out mass to make a star particle. And so this can for some time sometimes increase the magnetic field slightly, but it just adapts very quickly. So essentially the like the magnetic field always ends up where it wants to be dynamically independently of what you do with star formation, because there's not enough of the mass going through star formation quickly enough to change this massively.
So diff B is okay, yeah?
Well, so yeah, so the solver is so robust that it like fixes diff B very quickly.
Mm-hmm.
Like with a handful of time steps.
A dot B may not be then, by the way. There's a paper with Scanapico of 2020.
Yeah, like the problem is we don't have A. So it's
but that's it's not a problem in principle, because the magnetic field has its own A. It knows what it is.
Okay, yeah, thanks. The next is Volker. Volker, please go ahead.
Yeah, hello, Rudiger. Very nice talk. And my question was, you showed this results of book 2021, and I think you say that the cosmic ray diffusion with cooling by alpha waves makes I think the stellar disk larger. I think you shown that the halo is smaller. So does it just mean that if you have the cooling with alpha waves, you have no galactic wind, and so you have more accretion? Or
so the main difference is so in those simulations we always have still the effective model for the galactic wind on, so the cosmic rays only come on top of this. In those simulations, cosmic rays, we've played a little with it, and there's like a million reasons for this. But like if you switch the effective wind model off and just run with cosmic rays, it's like you just get nonsense. Like it's not strong enough to still make these galaxies. But it's like a very different topic. So the main difference between this Alfvén cooling versus not Alfvén cooling is whether the pressure in the halo becomes completely dominated by cosmic rays or not. Because if you become completely dominated by, like if the cosmic rays can diffuse into the halo without having to pay a price in energy with this, then you can put a lot of cosmic ray energy into the halo, and then the gas can just like the thermal energy becomes irrelevant because the hydrostatic equilibrium is completely supported by cosmic ray pressure. And then the stuff could just like does weird things. And so this, like in this case, you then like change also again the large scale flow patterns in the halo, and then you make a significantly smaller disk.
Yeah, for me, this would also sound unreasonable. That, I mean, I would say normally we argue something like our observations indicate something like equipartition between the cosmic ray and the thermal gas.
If you can exclude this from observations at like a radius of 50 kpc or so in the halo, I would be very interested.
Yeah, 50 is hard, say up to maybe 10, 15. This is what.
Yeah, but then you're still in the disk range, right? So like anything can be there.
Yeah, unfortunately, we're still limited there by sensitivity and basically electron aging.
Yeah, so thanks. I mean, there are few hands still up, but I'm sorry, in interest of time, we'll just move to the next talk. Can these questions be taken up on Slack, and Rudiger, please can take it up there. So the next talk is by Ellen Zweibel. Ellen, can you please share the screen?
Right. It's nice to see everyone. Thanks for the invitation.
Yeah. So Ellen, at 18 minutes, I'll just switch on my screen and give you a 22-minute notice.
Fine. Okay, I'll be very quick. I was asked to talk about cosmic rays and magnetic fields in the multiphase interstellar medium. I've had wonderful collaborators over the years in this area. I'm particularly going to highlight work by Chad Bustard and Evan Heinz in this talk today. So why is this interesting? So we've seen exciting global simulations of galaxy formation and cosmological simulation, but there are special dynamical and thermal effects that arise when we have a multi-phase treatment of diffuse gas in galaxies or galaxy clusters. And understanding these is is also key to interpreting observations of cosmic ray-driven chemistry, non-thermal emission, gamma rays, synchrotron radiation, which are key themselves to mapping magnetic fields, and also testing models of cosmic ray interactions with the ISM, because as you heard in the preceding talk, these can be very important. So there are some current challenges that we've not yet overcome in this area. So one, which is really not my own work and I'm not going to talk about, is that the low energy, by which I mean tens to hundreds of MeV cosmic ray spectrum as measured by Voyager just outside the heliosphere, really underpredicts the cosmic ray ionization rate that's determined from chemistry in the cold interstellar medium. So this would imply that cosmic rays are getting into cold clouds more than we might expect, but models of star formation feedback, which include cosmic rays, overpredict the gamma ray luminosity, which kind of goes in the opposite direction and suggests that cosmic rays need to be kept out of where the gas is. So these two issues have not been reconciled. Okay, so what I'm going to do in this talk is give a very short review of cosmic ray self-confinement, which is the theory that I'll be assuming. And then I'll talk about two things. One is the effect of cosmic ray transport on Parker's instability. And the second is the whole bottleneck phenomenon. And I've included links here to a few of our papers that give a more complete treatment. So the cosmic ray spectrum. I love this particular slide because it shows how many experiments go into determining the spectrum. You can also see that cosmic rays are mostly protons, et cetera, and that the spectrum extends over many, many orders of magnitude as a broken power law. So we know from observations that I don't have time to go into that at GeV energies, cosmic rays are confined to the Milky Way for about 20 million years. They're highly isotropic and scattered with a mean free path of order a parsec, and that about 10% of the non-neutrino supernova power in the galaxy suffices to maintain a steady state energy in the cosmic ray pool. So I'm going to focus on the GeV cosmic rays because they supply most of the cosmic ray pressure and are responsible for most of the dynamical effects. A lower energy cosmic rays do most of the collisional heating and the ionizing, and then the highest energy cosmic rays at an EeV or above are not even confined to the Milky Way. They must have an extragalactic origin or extra Milky Way origin. So the main agent of cosmic ray scattering is thought to be so-called gyroresonance scattering, which leads to diffusion. I'm going to give you a very quick capsule picture of it. So this red line here is a magnetic field that has large-scale curvature and tiny-scale structure, and the black helix is the orbit of a particle. So it follows the field pretty well for a magnetic structure that is on much larger scales than the gyro radius. And for very sub-gyro radius fluctuations, it kind of averages them out and doesn't see them. But if it turns out that there's structure such that one wavelength is the same as a cosmic ray gyro radius, or that it goes around once in one wave period, that's a so-called resonance condition. The interaction is very strong, and we can estimate just what that interaction is from a sort of geometrical argument. If this is the unperturbed magnetic field, and this is the magnetic field with a fluctuation delta B, then it makes an angle delta theta of order delta B over B naught. And if we define a scattering frequency as the mean square delta theta per delta t, and put in, based on geometry, what delta theta is, and set delta t to 1 over the cyclotron period, we get this scattering frequency, which is correct to order unity. And I would also point out that if the scattering is due to hydromagnetic waves, if the fluctuations are hydromagnetic waves, then it's nearly elastic because the Alfvén speed is much less than the speed of light. So the theories diverge over the source of these waves. And that's important So in the so-called self-confinement theory, the waves are generated by the cosmic rays themselves through the streaming instability. But you could also argue that the waves are just present as part of a turbulent cascade in the interstellar medium. This is confinement by extrinsic turbulence. And the main difference between these pictures is that in both cases, the cosmic rays exert a pressure gradient, exert a pressure force, but it's only in this theory where cosmic ray energy is being used to excite waves, which are then damped by the thermal background, that there's this collisionless heating that Rudiger Packmore alluded to. Okay, so in this classical cosmic ray hydrodynamics fluid treatment, which of course is necessary to model global systems like galaxies or even patches of the interstellar medium, the cosmic rays stream down their pressure gradient at the Alfvén speed relative to the thermal gas. They transfer momentum through their pressure gradient. They heat the gas through something that looks like friction, and they also diffuse with a diffusivity of order, so c over nu is the mean free path, and then you multiply that by the speed of light. And these models, or this theory, which was originally developed by Heinz Volk and his collaborators in the early 1980s, has been applied to shocks, to interstellar and intercluster heating, to the Parker instability, to thermal instabilities, galactic winds, and galaxy formation. So it's become a widely implemented theory. So let me just say a little bit about how the treatment of cosmic ray transport really matters. So this is a comparison from some work I did with Mateusz Rostkowski and Karen Yang several years ago. This is a model of galaxy formation. For the galaxy formation mavens, we followed the treatment by Salem and Brian and Salem. And so what we're looking at here is gas density in a galaxy model seen edge on. And here we assume that the cosmic rays are frozen into the gas and just advected with it. This corresponds to confinement by extrinsic turbulence with a very small diffusion coefficient. And what happens here is that the disk is puffed up by cosmic ray pressure above its natural scale height. That turns out to have a big effect on suppressing star formation, but doesn't drive a wind. If you allow the cosmic rays to stream at the Alfvén speed, boom, you get this big wind, you get this big outflow from the disk. So which model of cosmic ray transport is correct makes a big difference. I think there's good evidence, or at least theoretical evidence, that self-confinement at GeV energies is correct in Milky Way type galaxies. When I started thinking about these puffed up disks, I began to wonder if they were stable. And so that led to some work on the Parker instability, which I'll talk about in a couple minutes. But I wanted to point out a further wrinkle in this whole issue of how cosmic rays affect star formation feedback, which is that in cold, mostly neutral regions, the waves which scatter the cosmic rays are very heavily damped. And this is true whether the waves are self-generated or part of an extrinsic turbulent cascade. And so here's a comparison, work led by Ryan Farber, of the star formation rates under 3 different assumptions of cosmic ray transport. So in this model, the cosmic rays are just frozen into the gas. And there's a very strong suppression of star formation, basically because the mean density of the gas is reduced by cosmic ray pressure. In this model, we assume that the cosmic rays diffuse rather than stream, and that the diffusion coefficient is the fiducial value taken for the Milky Way, 3 times 10 to the 28 centimeters squared per second, and you get considerably more star formation. But if you assume that the cosmic ray diffusion coefficient is larger, about 30 times larger in cold regions, which are presumably also weakly ionized, you get even more star formation. So which of any of these treatments is correct is an important question if you're interested in star formation feedback and the role of cosmic rays. Okay, So let's get back to the stability question. Let me just review for you the Parker instability. So here we have the galactic plane with some gas clouds on it and a magnetic field that's initially stratified and tangent to the plane. And if you make an undulate perturbation of the magnetic field lines, then gas is free to flow toward the plane under the force of gravity. And so that's the free energy for the instability. And but it must work against the compressibility of the gas. So it takes work to compress the gas. And so the equation of state for the gas is a key parameter in assessing the importance of the Parker instability. So Parker published his paper in 1966, and the first stirrings of the cosmic ray self-confinement theory were published by Kulsred and Pierce in 1969. And so Parker assumed that the cosmic rays behave like a gamma equals zero fluid, that it takes actually no work to compress them. They just slide down the field lines at the speed of light, and no energy is required to make that happen. But if you treat the cosmic rays instead as a gamma equals 4/3 gas that's convected with the gas, it turns out that they're very stabilizing. And so we saw this in some work by Evan Heinz. So this is a growth rate plane for the Parker instability. I hope you can see that the two color tables here are different, but even if you can't see that, you can see that the domain of instability is, and the domains actually are also different. So the part of parameter space which is unstable, and the rate of growth of the Parker instability are drastically reduced if we compare the gamma equals 0 case and the gamma equals 4/3 case. So remember, this corresponds to strong confinement by extrinsic turbulence. If we put in cosmic ray streaming, the instability actually goes beyond the gamma equals 0 treatment which was classic Parker, the original treatment. So here, the domain of instability is much larger, the growth rates are much higher. And we've done nonlinear simulations that I don't have time to talk about, which corroborates this and shows that diffusion also can destabilize the system, cosmic ray diffusion. Okay, so the message here is that cosmic ray transport, which theory of cosmic ray transport is correct, is very important in studies of star formation feedback and the role of the Parker instability in structuring the galactic disk. Now I want to switch to the bottleneck story. So in the self-confinement model, the cosmic rays are streaming down their pressure gradient. They excite waves, which scatter them and keep them at a state of marginal stability. And in that state, you can show that the cosmic ray pressure varies with gas density to the 2/3 power along a magnetic flux tube. This is kind of a consequence of continuity. If the gas density goes up, the cosmic ray fluid slows down and builds up its pressure. So this picture carries the seeds of its own destruction. And this was predicted by John Skilling all the way back in 1971. He said, well, what happens if the gradient of cosmic ray pressure and the gradient of density are anti-aligned? Then the cosmic rays want to follow the gas, but that means they'd be streaming up their pressure gradient. What happens? So it was, and this is really not an idle question. One of the reasons that I wanted to work on this is that thinking about cosmic ray confinement in galaxy clusters where the magnetic field lines are tangled, demonstrably tangled, and kind of dip in and out of regions of higher density, you get a huge headache. So where do the cosmic rays stream in a situation like this? So we considered a simpler problem. So now I'm going to talk about work by Josh Wiener, former postdoc, Peng O, and Mateusz Waskowski, and me. And the general situation we considered was a cosmic ray source, which is magnetically connected to a cold interstellar cloud embedded in a hot medium and in pressure equilibrium with it. So let me show you some 1D results first. So when there's no cloud, we turn on the cosmic rays, and this front moves out over time. And in about 1 alphane crossing time in the system, which turns out to be about 6 megayears, you get this nice cosmic ray pressure gradient or energy density gradient, which is established and conserves this quantity, P cosmic ray over rho to the 2/3. That's this green line here. It takes a little while to settle down to it, but eventually it does. So what happens if you put in a cloud? So we put in a one-dimensional cloud with a hyperbolic tangent profile. Here's a dip in the alphane speed. And what happens is that between the source and the density maximum in the cloud, the cosmic ray pressure just goes flat. Then when it reaches the maximum, it re-engages. You get a very steep cosmic ray pressure gradient, and then it settles down to something on the far side. So what's the consequence of this? Well, so there's this acoustic forerunner when the cosmic ray source is turned on, and two things happen to the cloud. This steep front, where the cosmic ray pressure gradient was large, as you saw on the preceding slide, is a site of strong heating, and that erodes the cloud. So the density maximum is pushed backwards, but the cloud is accelerated forwards by the combination of thermal gas pressure and cosmic ray pressure. And if you turn off the cosmic ray heating, essentially by assuming strong cooling, taking an isothermal equation of state, you can see that this cloud is kind of set into motion. And these bumps here are not the result of some under resolution, but they're actually waves within the cloud propagating back and forth. So we thought this might be a promising mechanism for cosmic ray driving of both cold and hot gas in galactic winds, which is actually what's observed. On the far side, where you get the strong cosmic ray heating, you get a couple things. You get this very steep temperature profile. You find a cloud which is actually pressurized by cosmic rays, and the thermal gas plays a relatively small role. And this is a great laboratory for comparing with observations. So these black data points are from some work by Bart Wacker on galactic halo clouds. And here are various models that have been made to explain these ion ratios. And cosmic ray fronts do about as well as the other best model, which is a cooling flow. Conductive interfaces and collisional ionization equilibrium actually do very poorly at explaining these ratios. So we haven't done anything more with this. It's a very high resolution problem, but we thought it was promising. So now I'll talk about some later work by Chad Bustard. So this was actually published in 2021. Sorry about that. So we looked at a couple of things here. So the cloud is partially ionized. The ambient medium is fully ionized. So if you take into account that the waves are actually only coupled to the plasma, not to the neutrals, the alphane speed actually goes up, and you get this kind of stair-step profile. So flat cosmic ray pressure, a drop, flat in the cloud, and then it re-engages here where the cloud ends. The other feature of this is that it takes high resolution to model. What we found is that there needs to be about 10 cells in this front to get converged density profiles for its structure. Obviously, this is a problem in global simulations. This has to be put in some sort of subgrid way. We don't know what it is yet, but it's important because it controls the size of this step. You can see that there's a much bigger step going from the outside the cloud on the near side to the far side than there is in this situation. So getting the momentum deposition right for the cloud, which is sort of a mesoscale problem, really requires resolving the microscales. Sobering thought. So we went into 2 dimensions, and actually eventually to 3. And here I want to show you that the strength of the magnetic field is also an important quantity in how the system behaves. So if the field is strong enough, it's really very much like a 1D situation. The field lines remain straight. The cosmic rays are, cannot go around the cloud in any way, and they build up behind it. If you have a weaker field, I hope you can see that the field lines are just kind of warped around. So you get these lobes of cosmic rays trying to force their way ahead. And then eventually the field comes back. Of course, we get some numerical reconnection, but I think qualitatively, this is a picture of what we see. So we looked at how much momentum could be given to the cloud, and we looked really under 2 different assumptions. One is that the ionization fraction is 1, so you don't get this increase of the alphane speed inside the cloud. And here's the momentum as a function of time for this large group of different field strengths. And you can see that there's kind of a maximum field strength here, which corresponds to 5 microgauss. So it's not the strongest field, it's not the weakest field. And this is where you get the most momentum. If you put in weak ionization, the total momentum deposition is lower by about a factor of 2. And the ordering here changes slightly. And we discussed this in our paper. So then we thought, well, what happens if you actually have a clumpy medium, not just a single cloud, but many clouds? So now the geometry's changed a little bit. The cosmic ray source is down here. These contours represent density excesses. We had a sort of a simple model for making clouds. So white is, I think, 10 times denser, then there's yellow, then there's red. Red is 100 times denser. And so you can see that the cosmic rays actually kind of flow around this ensemble of clouds, and you are getting a whole line of bottlenecks, a whole bottleneck region here in this clumpy medium. What's the momentum deposition? Well, it's... Oh, okay. Okay.
Yeah.
Very quick momentum deposition. What about gamma rays? As I said, this is a big problem in comparing simulation and theory. The distribution of gamma rays so here, it's this ionization fraction question. Here, the cloud is very weakly ionized. You can see that the cosmic rays have gotten a lot further in than back here. So you think, well, maybe this is the solution to the problem. And so here is a kind of summary of all of the gamma ray emission in all of our models. So there are lots of different clump models. There are lots of different transport models. This is blown up here, and none of it really makes a huge difference, which in the end was sort of disappointing. So qualitatively, what you could collectively call fast transport, either a high diffusivity or a low ionization fraction, will reduce the gamma ray flux from a model, but that comes at the price of less of a dynamical effect from the cosmic rays. So at this point, we don't know how to have it both ways. We don't know how to have a lot of cosmic ray feedback and not a lot of gamma ray emission. We haven't solved this problem. Okay, so here's my summary. So I hope, if nothing else, I've convinced you that the details of how cosmic rays are coupled to the thermal gas that hosts them really has big implications for star formation feedback, launching galactic outflows, interstellar structure, maybe the galactic dynamo, although I didn't talk about that. And it's very important to test the theories of how cosmic rays are coupled to the gas with gamma ray data, which we and actually Phil Hopkins' group at Caltech has done a lot with this. Nobody, as far as I know, has done very much with the non-thermal radio continuum data, which I think is a great problem. And there's been quite a lot of work done on the low energy cosmic rays, and how that applies to the high energy cosmic rays, I'm actually not sure. So I think there are a lot of good problems here. We need to understand in my view, we need to understand what's going on at the small scales, and then figure out what the implications are for the mesoscales, the cloud scales, and then the large scales, the global simulations. So I sort of have my hand out here because there are people here with all sorts of expertise, and I hope this inspires somebody to work or continue working in this area. Thank you.
Thanks, Ellen. People, please raise your hand for questions for Ellen. Yeah, Ellis, please go ahead.
Okay, do you hear me?
Yes, I do.
Excellent. So you mentioned the implications for gamma ray emission. I'm wondering if you've also considered the implications for X-ray emission, because I'm looking at some of these simulations, and it seems this cosmic ray bottleneck effect has implications for the multi-phase structure of the medium. So could this have any effect on things like charge exchange emission, the ratio of charge exchange to continuum emission in the X-ray band?
So I think that's a great question, and what I now wish I had done. So in our nonlinear Parker simulations, we made these phase plots where, so it's basically a two-dimensional density temperature plot with a color table that tells you how much gas is at that density and temperature. And we did not do that for these clumpy medium simulations. But maybe I'll just write to Chad and ask him if he still has all the data. He's the one who did these simulations. They were done with Athena. And yeah, I think it would be interesting to see that. I'm actually going to write to Chad. If you send me an email or something, I'll know how to
I will do. Yeah.
Oh, great. Okay.
Thanks a lot.
Thanks. There is another question by Volker. Yes, please.
Hello, Ellen. Thanks for this really nice talk. And I also like to that you point to this radio continuum, of course. And of course, we have tried to make really some very simplistic models. And so it appears that we at least can, with the radio continuum, distinguish galaxies that have outflows and that don't have outflows by looking at the cosmic ray electron energy profiles and spectral index profiles, where we simply say that the ones that have no outflows, they look like diffusion dominated. The ones that have outflows, at least their advection plays a major role. And the other thing is we also try to measure diffusion coefficients and with convolving the star formation maps to the radio maps, and try to also measure the energy dependence of the diffusion coefficient. So that's something that we can already provide with data.
Yeah, I'm aware of your work and your modeling tools, and so yeah, I think on the global scales. Now, what about something like this? So, I mean, do you think it would be worthwhile to try to make a synchrotron map of a more kind of local patch? And you can see where the field lines are here. You can see that they're kind of warped. You can see where the cosmic rays are. In a way, the electrons, the synchrotron spectra can be done with post-processing, because there probably aren't enough electrons to really affect the cosmic ray pressure. It's not highly coupled as the gamma ray, where if you include a loss term in the cosmic ray propagation, it can make a big difference to the dynamics, and so it's all highly coupled. So I don't know on how small a scale it's interesting to make synchrotron maps.
For the galactic emission, you can of course go to very small scales. So there is one paper that's not by me, but Christoph Frommer and some co-authors, they look at the non-thermal emission in the galactic center, and they think they find indication of streaming along magnetic field lines. So that's then on a fairly small scale. I think that's on a parsec scale. Yeah. So I think that that they call it the Christmas tree paper. Maybe I can find you that reference.
That would be great, actually.
Yeah, no problem.
I was just writing something.
Yeah, thank you. So thanks, Ellen. We'll probably move to the next talk now. Petros. Yes, can you please share your screen?
Absolutely. Hi there.
Hi.
You should be able to see my screen.
Yes.
Excellent. Perfect.
Full screen. Yes, please take.
Okay. So first off, thanks a lot, Amit and Luke, for inviting me to this event. Honestly, I really enjoyed all the talks up until now. I had to wake up at 5 a.m., but that was definitely worth it. This is going to be somewhat of a change of pace because we're going to be talking about something that is not in the title of the special meeting. So we're going to be talking about experiments and how they can actually allow us to get some more information on dynamo theory. Okay, so the work that I'm going to show you is the work of the T-Dyno collaboration. So this is a give me one quick second to hide this. Yes, so it's the T-Dyno collaboration, which is an international collaboration from many institutions around the US, Europe, the world, and it's sponsored essentially by numerous federal agencies in the US, the PSRC in the UK, and the European Research Council to study magnetized turbulence and astrophysical processes in magnetized turbulence using laser-driven experiments. So this is a rather new approach to the study of turbulence, and I'll try to motivate a little bit why this is of interest to astrophysicists and what can be learned from this. I'll start with a summary, so we'll not have to repeat this at the end of my talk. I will try to convince you that the fact that we have now high power laser facilities has essentially enabled us to, has opened up a new field of plasma physics research that is relevant to astrophysics in the sense that it can allow us to reproduce astrophysical environments in the laboratory, not just scale experiments, but also astrophysical conditions in small scales, of course. I will discuss in this talk the T-Dyno platform, which is an experimental platform that we designed using flash simulations in order to demonstrate fluctuation dynamo in the lab for the first time, something that we achieved at the Omega Laser facility at the Laboratory for Laser Energetics. And I will tell you how the application of this platform by our collaboration in a concerted fashion can actually shed light to numerous aspects of fluctuation dynamo in different plasma regimes, ranging from subsonic to supersonic turbulence, small and large magnetic Prandtl numbers, and get information like what is the magnetic field growth rate, what is the magnetic to kinetic energy ratio at saturation, what is the power spectrum of the magnetic energy and the kinetic energy, estimate perhaps the critical magnetic Reynolds number for dynamo to operate, characterize the intermittency of the magnetic fields that we can get. And of course, if we're indeed able now to recreate astrophysically relevant turbulence in a controlled laboratory environment, then we can actually use such a platform to study other astrophysical processes that are mediated by magnetized turbulence, things like heat transport, transport and acceleration of cosmic rays, and so on. So the answer to the question that I was presented by the organizers is essentially laser-driven experiments of magnetized turbulence in general can verify our theories, can validate our codes, can validate the observational techniques that we're using, because we can borrow them and apply them in these laser experiments, but also provides us with the opportunity to have new discoveries. And that's why I will say that this is an incomplete list. Okay, so let's start with the first bullet. And the fact that this advent of high power laser facilities, like the National Ignition Facility at Lawrence Livermore at the bottom left, or the Laboratory for Laser Energetics at the Omega Laser Facility at the top, has essentially opened up this new field of astrophysical research that allows us to create astrophysically relevant plasmas in the lab. And this is accomplished essentially by bringing in extreme amounts of energy in a very small volume for a very short period of time. If you take the National Ignition Facility, for instance, here at the bottom left, I hope you can see my cursor, this $3.5 billion facility is the most energetic laser that we have. It's a 10-story building. It houses 192 beams that can deliver something like 2 million joules of ultraviolet energy in the volume that is the size of a pencil eraser, which you can see here. And they do that in a billionth of a second. So this means that we have a ton of power to play with. How much? It's the equivalent of 500 trillion watts. This is 1,000 times what the US power grid has at any given point in time. While these facilities have been primarily built for ICF, so inertial confinement fusion research, and I hope that you've heard of the 1.3 megajoule breakthrough that the NIF had the past month, and also for stockpile stewardship research, so how to model nuclear weapons and ensure that our arsenal is safe and secure. They also dedicate a significant amount of time in fundamental basic science. And this makes sense because the conditions that we can achieve in these facilities is akin to what you would find inside stars or planets. So what is the concept here with respect to laboratory astrophysics experiments? The core idea is that we can use essentially the same ansatz, the same equations to describe the experiment that we could use to describe an astrophysical object. Well, if that is true, we can come up with a self-similar transform from one to the other, provided that the non-dimensional numbers that correspond to the various physical processes are large enough, both in the astrophysical system or the laboratory experiment, or at least that we can have similar values. And by non-dimensional numbers, think of Reynolds number, magnetic Reynolds numbers, and so on. And this is where laboratory astrophysics has been lacking for a long time until the coming online of these facilities, because things like the magnetic Reynolds number is actually pretty expensive to achieve high numbers of using experiments like liquid sodium experiments and so on. So, and here enters the T-Dyno collaboration. This is a collaboration that is co-led by the University of Oxford and Gianluca Gregori and the University of Rochester and myself, where we are essentially bringing in theorists, experimentalists, simulation folks, and observers to study magnetized turbulence, fluctuation, dynamo, and cosmic ray physics. Our contribution to this big collaboration is the design of these experiments using the Flash code, which we have developed at the Flash Center for Computational Science for the past 20 years, and more recently we have been extending it with the physics capabilities necessary for actually modeling high energy density physics experiments. So we can actually model all the processes in play in these experiments with our radiation and ET code. Using Flash and hundreds of 2D simulations and dozens of 3D simulations, we designed an experimental platform for the Omega Laser Facility that would enable us to generate magnetized turbulence with high enough magnetic Reynolds numbers for Dynamo to operate. And the configuration looks something like this. It's a bit of a busy diagram, but the target consists essentially of two composite targets, these foils and washers configurations that are placed symmetrically against each other. Between the two, we place a pair of grids. These are meshes, like we can sort of see it here. And we offset the two meshes in space in order to create, to break the mirror symmetry and essentially perturb the flows. What we do is we drive these targets with 5 kilojoules of laser energy from the back. There is a pair of flows that are coming through the grids, and the misalignment of the grids essentially allows you to shear the two flows and create a turbulent region in the center. Now, this whole target is the size of a dime. You can see the configuration here. And this is what we get from the simulation perspective. So what we have is Birman battery magnetic fields are being generated by the laser target interaction. The plasma plumes are expanding and they go through the grids. And you have these interleaving plasma fingers that shear and create this hot turbulent region in the center. Now, the magnetic Reynolds numbers that we are able to achieve in the simulations are indeed above the critical values of a few hundred that we've heard in previous talks. I mean, you know, having fluctuation dynamo operating in simulation is not something new. What was new was our ability to actually use a suite of experimental diagnostics in order to be able to see in the lab what we were actually getting. So just to give you a bit of primer in terms of the experimental diagnostics used in such experiments, we're using X-ray imaging. So we're looking essentially at the KV X-rays that is coming from the hot plasma in the center. And by analyzing these images, we can actually infer the fluctuation spectrum for the density, similar to what is being done when analyzing X-ray maps from galaxy clusters. We use Thomson scattering. So essentially, this is another laser beam coming in, and the light scattered off of ion acoustic and electron plasma waves can give us information about velocity, temperature, density in the volume where the scattering happens. And we have also modified it to include Faraday rotation capability. So we can actually measure the magnetic field by splitting the SMP polarization and looking at the rotation. We also see the magnetic fields using proton radiography. So we're using essentially a subset of the beams available to us in the facility. The rest of them are actually imploding a D-helium-3 capsule, and fusion reactions generate 3 and 15 emitted protons, which fly out from this point, go through the interaction region where the magnetic fields are present, are being deflected, and then we record them onto a screen. So it's essentially like a proton snapshot of the magnetic field topology. Using the reconstruction technique that we have developed, we can actually, and you can read about this in this article, we can actually recover the path-integrated magnetic field that these protons felt on their way to the screen. So the first two give us the plasma state, the second two give us essentially an estimate of the magnetic fields. And this is what we got from our first shot day. So the X-ray emission matched essentially the morphology predicted by the flash simulations. The analysis of the X-ray fluctuations gave us the 3D fluctuations of density, from which we can get something that is similar to a Kolmogorov spectrum. And from the Thomson scattering measurements, we were able to show that our magnetic Reynolds numbers were well above the critical Reynolds number that was predicted by theory in the small Prandtl number region, and therefore Dynamo could actually operate. In the proton radiography, we actually saw the creation of these filaments. The stochastic magnetic field is quickly developed in a matter of 5 nanoseconds, which is about a couple of eddy turnover times at the other scale. And combined with the Faraday rotation, we're able to demonstrate an amplification from about 4 kilogauss to about 100 kilogauss RMS at saturation with peaks about 450. So the end result was essentially a magnetic to kinetic energy ratio of about 4%, which is a small value, but the peaks of it actually were about 0.5, which is consistent with an spatial intermittent stochastic magnetic field configuration, which we will characterize in a bit. So this achievement essentially allowed us to launch a concerted effort to study magnetized turbulence for different astrophysical systems in different conditions and in different facilities. This is a snapshot of the various efforts that we have ongoing, and I'll be talking about some of the results that we have recently published and are to be published. I will not go into details on things that are currently under review. I'll point you to preprints though. So the great benefit of this platform is that it is very versatile. It's really easy to redesign using class simulations and optimize for the conditions that we aim to achieve. This is done by essentially controlling things that like the magnetic Reynolds number, the Prandtl number, the length scales, through modifying things like the foil thickness, the doping and material properties, the laser drive, and the grid specification. So we can actually move in different plasma regimes rather easily by taking advantage of design specifications. The fact that we've come up essentially also with a configuration that is very easy to align, so we can take advantage of the high repetition rates in these laser facilities and actually get time resolved measurements of what is going on. These are the results from our recent paper on the Proceedings of National Academy of Sciences, where we were able to show time resolved measurements of fluctuation dynamo in the Prandtl number or the unity regime. And the time resolved measurements allows me to show movies rather than of experimental data instead of movies of simulations. And you can see here the formation of the turbulent region in the center, and also the evolution of the magnetic field as seen from the proton radiographs and the path integrated magnetic fields that we can achieve in the interaction region. Now, similar to before, by doing an analysis of the X-ray emission, we can get the power spectrum for the turbulent motions, and we recover again a spectrum that is consistent with Kolmogorov. We can also use this information to validate our simulation code, and these are the real and synthetic X-ray images with flash, and use essentially the same experimental technique onto the synthetic data in order to recover the profiles of the emission as we did in the experiment. Granted, this is a rather limited range, so we have experiments lined up for 2021 that will be extending this range by a factor of 10x, and more information will come there. But the very interesting aspects of it is the fact that we can actually get time resolved plasma properties and see how the turbulence is set, compare all values with the flash predictions, and try to understand what is going on in the experiment. What we see is essentially that we have a rapid onset of turbulent velocity in the plasma region at high temperatures, which are high enough to get to supercritical magnetic Reynolds numbers, and for the early times be in the Prandtl number or the unity regime. At late times, things are a bit trickier because the large density actually results in the laser probe to actually heat up the plasma itself. So the early times are safer to analyze. But we were able to demonstrate a Prandtl number or the unity regime at early times where we expect most of the amplification to occur. And this is where we can actually apply our analysis and get temporal evolution of magnetic fields. So if we know the path and we can tell it from the X-rays, we can actually recover from this path integrated magnetic field values the temporal history of the RMS and the peak magnetic field, and demonstrate essentially growth rates, which turn out to be of the order of 4 to 12 the RMS divided by the outer scale, which are actually larger than what is being observed in periodic box simulations of similar conditions, something that we attribute to a component of shear dynamo operating, and also get magnetic to kinetic ratios that are similar to what we were getting before. One thing that we were not able to match with the flash simulations, which otherwise predicted all of these conditions, was the correlation length. And you can see here the flash prediction versus the experimental values. And you can also see it by eye when looking at different times, the experimental data versus the synthetic proton radiographs undergone through path integrated magnetic fields analysis in these plots. So what we see is actually that the integral scale that we obtain in the flash simulations is actually closer to the results that periodic box simulations were getting before than what we have in the experiment. In the experiment, we get a factor of 2 to 3 larger than before. So we can actually see the temporal evolution of the spectra in the flash code, recover the k to the 3/2, the -5/3, and also compare with previous periodic box simulations. But the end result is that the experimental data actually have an integral scale that is significantly larger than what was being predicted by our simulations, which is an intriguing thing given the long-standing problem with the scales of the magnetic fields present in the ICM. There are various possible explanations which we will try to address, but this is for future experiments. Another thing that we can actually recover is spatial intermittency. So the 4% BRMS over kinetic energy RMS is actually small, but it turns out that there are a number of points in the interaction region that the magnetic field is dynamically important, and you get equipartition locally. We can also see the degree of intermittency and measure it using this filling factor technique that we talk about in this article, and see how this deviates from a Gaussian distribution. But it essentially we can quantify in time the evolution of spatial intermittency.
It's 22, yeah.
Okay, I'll wrap up by saying that we have started a concerted effort to study supersonic turbulence as well, and with experiments at RAL and LMJ. However, we have not yet been able to demonstrate supersonic dynamo in the lab, and we have been able to show conditions that are relevant to essentially magnetic tangling. The amplification is apparently less efficient in supersonic turbulence rather than subsonic, and this is a preprint of a paper that is now accepted for publication. And I will say that we have simulations and experimental results from our most recent days of studying fluctuation dynamo at omega, which they aim to bracket essentially the critical magnetic Reynolds number for supersonic dynamo that was predicted by Christoph. I will not show any of those results, and I'll just point out that there are also some papers looking into other astrophysical processes in magnetized turbulence that might be of interest for folks here. I'll stop here and take any questions.
Thanks, Petros, for this very interesting talk, an exciting field of laboratory astrophysics. Are there questions for Petros? Please raise your hand. Kandu, yes, please go ahead.
Yeah, very interesting that you can simulate the fluctuation dynamo in a laser plasma environment. You talked about suppression, I think, of heat conduction. One question which has always bothered me is what happens to the resistivity in the presence of all these small scale fields? I mean, Alex Shekushin always discusses viscosity and people always discuss thermal conduction. But do you also have some handle on, you are using a Reynolds number and some eta. Is the plasma just collisional or collisionless, or what's the kind of plasma that you have?
Right. So the type of plasmas that we create in these experiments are, for the most part, very much collisional. While the initial interaction happens, while the two flows first collide, there is some interpenetration due to at least in the NIF experiments that are being discussed in this preprint. But for the majority of the vast majority of the experiment, the turbulent plasma is collisional, and we're at least in our modeling we're using anisotropic magnetic resistivity, and most recently we have included very up-to-date transport coefficients that are rather accurate in that description. And there is a paper by Jonathan Davis in 2021 that discusses these types of transfer coefficients.
Right. So when you're saying the thermal conduction is affected, that's basically due to the suppression of perpendicular. So
no, it's actually much more than that, and it is very interesting because in these experiments, what we're seeing is a suppression of the order of 100 or more with respect to the Spitzer conductivity, and we think it is related to instabilities happening, like kinetic scale instabilities at the very smallest scale. So there is some at least from a simulation perspective, the only way that I could reproduce the fluctuations of temperature that we're seeing in these experiments was to switch off completely the thermal conduction, and it is consistent with. It's really interesting because it's essentially what we're seeing in cluster plasmas. So I'm curious to see what we're going to get out of it. We actually have a follow-up experiment at the National Ignition Facility next year to look at more detail the thermal conduction in these plasmas.
Sorry, but the cluster plasma is collisionless more. So that's why was my first question.
No, that's right. That's right. What we're trying to understand is the microphysics in the smaller scales, right? So if you go below the dissipation scale of the viscous dissipation scale, there are some processes that Alex Shekushin has theorized on why we might be getting this type of.
Okay, I'll look at the papers and we'll see. Thank you very much.
Thank you.
Thank you. I don't see any hands up, but there's a question in chat. Do you get jets or just spherical expansion after the field has been formed? From Paul.
So are we talking about the interaction region or about the? Which jets are we talking about? Because there are essentially jets being formed by the drive, which are moving inwards. And then once you have the collision, you're forming this turbulent interaction region that expands radially outwards. So you do get fast flows that are moving, and it's essentially an expanding disk. So any homogeneity assumption, actually, isotropy assumption is good for the innermost radii of this disk.
Thank you. Thanks, Petros. I don't see any questions. Maybe we can continue discussion over the Slack. And I think that brings us to the end of the meeting. We had a discussion session too, but I think the point is this Zoom is managed by RAS and there is another meeting starting off. So there are a few points. I would first like to thank all the speakers, and all the speakers of also pre-recorded talks who took effort in, you are basically the meeting. That's the way I think it. Invited speakers plus pre-recorded talks is the meeting. And then I would like to thank the audience for joining in and very good discussions we had. Also, I would like both pre-recorded talks and speakers today were happy to accommodate our request of the specific questions which we just created to excite some discussion. So for people who are interested in discussing some more or some social catch up, we can go to this Zoom after party thing which I've created. The details are on Slack. I'm also putting details on the chat. So I will move out, but Luke will be around for a few minutes if you want to use the details on the chat. So the chat will be active. And I thank you all again for this wonderful discussion. I suggest if you have time, please join the other chat, other Zoom link. The details are given in the general channel of the Slack and also in the chat here. Thank you all. See you on the other side.